Hello, and good morning, afternoon, or evening, depending on where you are. This is day 3 of the Eddy Symposium, and I'm going to just have a short discussion here about what I thought some of the interesting things coming out of the first few days, and then we'll have maybe 10 or 15, 20 minutes with some open discussions and maybe some hopefully input from you on Slido on things that we're doing for the rest of the symposium. So next slide. So here are a few of the takeaways that I had from the first few days. I think we had lots of very interesting speakers, and so it's a little hard for me to pick out some points because I thought everything was excellent. But there's a few things that struck me was sorry about that. My headphones decided to drop out. As I was saying, Gavin started out with mentioning that solar terrestrial physics is by its nature interdisciplinary. We need to be historians, geologists, energy physicists, chemists, social scientists, and so we can't have the in-depth knowledge that we need in all of those areas to really tackle these problems. And so this requires collaboration. And we've seen many talks about how the nature of that collaboration is changing, especially over the last, say, 5 years. We're really seeing that open science and co-development are becoming a key part of what we're doing in our science every day. And I think that we need to recognize that those that are participating in that and contributing to that need to have their efforts in that area rewarded. The other thing that struck me is computation is becoming a very large portion of the science we do, whether it's analyzing big data or running large models. The data volumes have just gone up astronomically. So that has become quite a change, I think. We're probably data rich these days. So as a result, there's this explosion in the number of tools that we can use, and the difficult part I see is that knowing what is the appropriate tool when we're tackling these problems. And so I think one of the hardest decisions maybe is sort of where do you put your energy and what tools, how do you discover these tools and determine which ones are the right tools for the job. Next slide. So one of the interesting, obviously, issues that we have that we're all trying to deal with is how do we use big data. And I think big data, we had a nice talk that sort of highlighted some of the challenges with using big data, and that include things like, the data that we get has probably been underfunded in terms of its preparation, in terms of understanding its quality, making it available, and the publications around that data. It's often tempting to launch a satellite and get the data, and then we're always complaining that the analysis side of it is perhaps underfunded. This data is typically very complex, lacks absolute calibration, and is heterogeneous. We may be trying to combine data on different scales at different temporal resolutions, And so that is a challenge in how we combine data sets. These data sets can be, for a model such as would contribute to the climate activities like CMIP, where you're talking petabytes of data. And so the old model of downloading the data to your local workstation and analyzing is just not sustainable. So we're really changing how we access this big data. And sometimes when we, for example, the example of TEC data, it's very dense over where you have receivers, but in the middle of the ocean you have no data. So we may have large volumes, but still not enough to tackle a scientific problem. So how do we overcome those issues? And we need to start moving into the cloud. We need to start using HPC in order to start analyzing these large volumes. So how do we do that? Well, if you're new to a scientific problem, we had some nice advice there that start small. Unit test your analysis workflow. So you can start out with some idealized data sets and see if you get the right answers from that. Make sure that if you're running a model, that you're getting the right output as you run it, and so that if those people providing models can provide validation data sets, that's going to be very helpful. And don't necessarily lock yourself into a particular data science method. Look at several and see. The other thing is when you're using observational data, the first step should always be to engage with the PI, I think. And even on the modeling side, sometimes I see papers, the first time I see that my model output has been used is when it shows up in a publication. And so there's always a fear there that it's being used inappropriately. So I think really think about engaging with the PI. And one of the most exciting things I think of the last few years is the ability to harness the power of cloud computing. So things like Pangeo, Dask, and Jupyter really are transforming how we're looking at data set. And I always tell people that I work with, don't move the data, take the analysis to the data. So leave all of those terabytes of model data where they are and run your analysis code remotely and access it. And one of the other points is I think we have a tendency, this is a hilarious cartoon, to try and reinvent the wheel and think that we can do it better than the previous person, but then we may end up only getting as far as the previous person did and not really completing things. So this idea of reusing and resisting the temptation to build something new is something that should be kept in mind. Next slide. So I think that last point was the first point in this paradigm used by Pangeo about how to build this ecosystem for analysis of data and to do science. And I really think that this could be a way in which something we might want to embrace in our community. And this idea that we would reuse the data, we would use this modular ecosystem and integrate our individual efforts within an ecosystem, documentation so that other people can use it. We often say, oh, well, I have my code for research, and then I have the code I give to other people, and we never try and from the beginning start to try and document our analysis code. But if we are always thinking when we're writing code about how it could contribute to other things, maybe we would think about writing our code slightly differently. And obviously, anything that we do, if we can put that back into the ecosystem to contribute, and it becomes a two-way street then. So this is one way. I think it'd be really interesting a discussion about whether this sort of pattern is something we could adopt. And again, I think we should think fundamentally about not trying to replicate this system that may be extended. So it's not like, let's not try and build our own system, but take this infrastructure and maybe work within this infrastructure and just extend it from the earth sciences out to the solar terrestrial physics. So next slide. But I think overall, there's been a lot of discussion about scientific, and data analysis, data science, and that. And we had some really good, nice science talks as well. And I think that we do need to maintain a science focus. I think Ryan said yesterday, data science needs a domain. And so we should always be thinking about not just developing new hammers, but always thinking about what are we trying to achieve, and so we should bring this back, I think, to some of the science problems. And I think there was Peter gave a sort of threw out an idea here that in his talk that we have great facilities, and we're building larger and larger instruments, but if we departed too much from defining key remaining solar questions and acquiring specific tools to answer them. So I think that's a good cautionary point there, and we should take that to heart. We also need to consider what are the tractable problems, I think, and such things as, are there fundamental limits on prediction, is one of the questions I think is an interesting question. With the example of this chaotic water wheel, maybe we can't predict things, but I think there are ways around that, such as thinking about moving from being able to predict a particular event to a statistical prediction, and I think that's done in weather, and there's still use, I think, in understanding the statistical nature of extreme events and how we might be able to provide useful information. And providing that useful information is something that I think we should be aware of. There is definitely room for fundamental research that doesn't have a direct application, but also there are pressing societal needs out there, and so I think we should be looking at those and see if we can meet them. While we're doing all this, our scientific culture needs to, I think, change a little bit. We need to understand, there's a question of when we're starting to use AI or machine learning, do we trust those results if we can't necessarily point to the exact causality in a chain? So we have to develop scientific trust in these new tools, and also reward this co-development in terms of things like promotion and that sort of thing. Next slide, I think. So a goal for today, I'd like everyone, if they could, to contribute to the discussions on Slack, and also within this time that we have now, to feel free to put some ideas into the Slido and use the upvoting button if you see an idea that you really like to help have those percolate up to the top. I think a measure of success of this symposium will be how it initiates cross-disciplinary collaborative science. So I'm really hoping that from this, we begin to develop working groups, we start writing some white papers, and we really start to organize the community in this sort of cross-disciplinary, with this cross-disciplinary focus. So there is a channel on Slack. I hope everyone has signed up for Slack, called Final Collaborations Ideas, and we're going to have breakout sessions on Thursday. And so we'll have a limited number. So really we'd like to see some discussion about what those sessions should be around. And then by the end of today, we'll sort of define those topics based on your input, and those will be the breakout sessions for tomorrow. So there are some interesting ones that have already been posted, such as, can we use machine learning to reconstruct historical sun climate data? Back to Peter's point about should we be thinking about designing a small scale instrument with a very focused science question? And the point that I sort of made earlier, that I think that should we be extending or developing these collaborative tools, these open science tools in our field, and could we have an activity around that? So I think that's it. I'd like to open it up to discussion. And and maybe everyone can unmute that is online now and share their camera, and we could have a discussion. Ryan will be monitoring the Slido, I think. Ryan, so if there are questions that show up there, because I can't see them here, but any thoughts? Lika, maybe you can start off.
Well, Dan, I'll jump in and thank you, Lika. If you don't mind, there's a question that I think it'd be a good place to start. It's an open question, and thanks, Dan, for the nice review. I'm going to look back at the slides. There's a lot of good material in there. The question that we had was, how will we know if there's a fundamental limit to predictability? Is it due to limited data, to science, or something else? And so that is a big question that could go in the final collaborations channel for sure.
Mm-hmm. Yeah, it's when we're struggling across, I think, in all fields, earth science, the idea that, especially with this push now to try and go into this timescale between weather and climate. We can predict the weather next week. We can predict climate change. We know what's going to happen if we keep putting CO2 in the atmosphere in 50 years, but we don't really know what we can do in 10 years time. And that's where people actually want the information. They want the planning for infrastructure and those things operates on that decadal timescale. And so there's this big question about what can we predict on those timescales. And I think that same question applies to solar physics.
It seemed like, the question is really important, but in some ways it also seems like me to be one of those questions. It's the unknown. So while we strive always to kind of keep that in the back, just like we are doing, right? Explainability of AI, we also keep our focus on the foreground so that we can actually continue to make real near-term progress as well. So not get lost in such a big question that we are not prepared to find an answer probably anytime soon, but it's always there at the back of our mind. Just thought I'll share at least my own thinking on this.
Yeah, I would say that just to offer another component to that, it's an important perspective, Lika, that predictability is a very relative term, and so you really have to be pretty clear about what level you're looking at the system. So defining the scale, understanding and being explicit about the assumptions that you're trying to address is going to affect what the answer to that question becomes. So I think we need to be more clear about where we're starting.
I would agree with you. I think when we get to a point of defining topics, I think we have to understand whether we are addressing that topic because of its real science understanding. So prediction will come from science understanding, perhaps, but what the goal is. So sometimes there are topics that is purely driven by an outcome that we can use for societal benefit, for example. But sometimes, for example, the TESS example, right? Whether we have found another exoplanet in the next 10 years, for us, it's not a societal benefit in that sense. But indirectly, of course, it's a benefit because we have gained some new knowledge. So I think that's by kind of capturing first what are the areas, the topics that emerge, and then we'll go through the process of sort of bucketing them. And then the ones where there is direct relevance to society, it's almost like engineering product, right? You want to look at it very carefully, and what you, Ryan, mentioned, those items become very important because it really impacts us.
Yeah. Rajesh, did you have a comment? You can put something in the chat there.
I don't really have a comment. I'm sorry I didn't attend any of the sessions yesterday. Simply, I just didn't have time. But today we have a block of time. But your summary was really very helpful to me personally. And it's one thing to to talk about methods and tools and Jupyter and all, we live in that world and machine learning algorithms, and we have pretty smart people there. But until you connect them to the physical reality, you do not have not only the right problems to solve, you also do not have the right level of humility to solve that problem. And here is what I mean by that. I almost all the physical scientists I know, they know that whatever they're thinking could be completely wrong. None of the computer scientists I know has that thinking. And the reason is the world in which the computer, it's not because they are naive or they're arrogant, which is probably true, but mainly because they live in a world in which the laws are their own. And therefore, it is only a question of how good it is, or how fast it is, or how correct it is. But it is never that the electrons don't follow my emotions, which is what happens in physical world. And so part of the work that I do is keep bringing physical scientists, mostly life scientists, because the uncertainties are so many. But solar is probably the same way, where they have to keep saying, all right, this is the hypothesis, but we really don't know. And I can assure you, when you go to a typical computer science talk, you would not hear the term, I really don't know. I mean, they're just not there. The only unknown is Cook's theorem or undecidability, which is really a gross result of some kind, not really very useful. So anyway, so that's all I wanted to say, but thank you.
Yeah.
That is such an important perspective, right? As we are going through this exercise, I think sort of a change in cultural thinking.
Mm-hmm.
And culture means so many things. We have come to use the word interdisciplinary, diversity, culture in a very generic sense. We have siloed the words themselves into meaning something, right?
Mm-hmm.
In the way you described kind of the problem, that's a cultural mindset. How scientists in the physical world are trained to kind of ask questions and solve this versus how a computer scientist or data scientist would tackle it. And it unshackles you from that kind of burden and be more creative and imaginative. No, I just resonated with kind of the idea, the value that you put out. But this is how we are learning. We might not bottle it into one particular topic, but it will shape future thinking.
But a refrain I will give you, even for the physical scientist, is when you go to the other end of the spectrum, we also work with social scientists. And trust me, they use a bunch of black boxes, and then they jump onto conclusions which are totally, totally bogus. For example, how is a person going to behave? How is it going to react? And what is the effect of income inequalities on depression? And much of it is scientific bullshit. But they make those conclusions because they're backed by numbers. And so the problem now for scientists is much of the science today actually is communicated over forums like Twitters and social media. I mean, you can only see the vaccines and all the stuff that's going on with Corona. That is subject to such social science experiments, people taking pieces out, and therefore very wrong conclusions made. And so one of the things is the scientific society. I'm now being Bill Bryson for those of you who read. Bill Bryson connects the dots between scientists and science. And that social effect is going to have an impact even on the harder score scientists in terms of how they think about things. You get a short Twitter from a very famous scientist and so on. It is taken out of context and so on. And so there are lots of examples of that. And this is becoming a real danger for data science, because people are, quite honestly, companies are taking resume screening services through AI. It's like predicting who will perform how, and humans are probably the ultimate uncertain entity in terms of the trajectory they will take. So
Ryan, you had a comment?
Yeah, I appreciated Rajesh's use of the word humility. I think that's very important. And I think kind of where that relates to the quantitative aspect of this is how we do uncertainty quantification. What do we use to put error bars on what we put out there? I see too often studies that have one value as the answer or the result that's presented. And I think there's a lot of room for understanding what the uncertainty that goes into that is. And we've talked a lot about machine learning. And I think that it's still a budding area of research within the machine learning community itself about how you track uncertainty through those models. And so I think that the sciences can give a nice use case for trying to innovate in that space. And it kind of gets back to something that I think is really important. It's that as scientists, our job is not just to use the machine learning models, but also to feed back knowledge to those communities about how to improve those and use those more effectively and rigorously. I know that a lot of machine learning practitioners they need use cases to test new models and to better understand those models. And as Lika mentioned, to try and develop some level of explainability of these models. And I think the sciences can provide that in this kind of symbiotic relationship. So it's not just.
And I think that you could also extend that actually to physics-based models, not just what comes out of these black boxes. Sometimes I get people that are surprised that the latest version of our model gives different answers from the previous version of our model, and they say, well, what's the difference between Wacom 4 and Wacom 6, and why am I getting a different answer here? And the idea that even our physics models parameterize processes, and what we call structural uncertainty, how you put that model together, creates differences in the results, and you have to understand that uncertainty when you start thinking about predictions from these models. We've moved now from single realizations to running ensembles, say 20 realizations of the model, and we're doing a better job, I think, of conveying that uncertainty from the models, there's maybe a temptation that the model is truth, and no, it's not. We have to deal with that uncertainty from what's coming out of the models.
Even I want to add, for this AI or machine learning, we also need to pay very good attention for data quality, what type of data is going in, because that determines the output. If you put a garbage data, whatever outputs may not be real. And so one needs to have some physical understanding also where it comes in a play, what input parameter goes in, or training or predicting.
Phil, I saw you had a comment on Slack about the ethics of societal needs. You want to comment on that one?
Yeah, I have often noticed in my years, several decades as a scientist, that sometimes institutions will ask for answers to what I think seem to be, to me at least, unanswerable problems. So, for instance, NASA would love to provide the world with a direct indicator of an incoming CME with its magnetic field pointing in the wrong direction such that it's likely to do something. And they want to have at least 24 hours or maybe 48 hours to shut everything down. While I think it's important for us to try and reach those goals, I think it can be a little irresponsible of us to promise too much. And this can serve, I believe, to undermine trust in science. And trust in science for me is at a crisis point. I've never seen it so low, at least sitting in the United States, in the society here. There are sociological problems involved with all that. It's not just trust in science, it's trust in anything. But I think, so my question was really, if we are under pressure to predict something, what do we do? Do we just accept the money and try and do it? Or do we say, no, I I think we need to do something slightly different. Anyway, those are the kind of thoughts that I was worrying about. Nothing specific towards the goal of creating a collaboration at this point. That will come tomorrow, I hope.
So I think we are almost at the end. I just kind of like Dan to put up his last slide, which was a goal for today. The conversation is fabulous, and I think we need a space to have exactly the conversation that is going on. But for us, also to create topics, if you look at the ideas posted already, reconstruction of historic sun climate data, using AI/ML, designing a small instrument around a focused science question, or creating open source tools for Earth and space science. These are kind of broad buckets. If we can put some ideas into these specific bins, then agencies might be able to help support those concepts also. Thank you.
Thank you, Lika. Okay, so I think we should get the talks going now. And the first talk is by Sophie Murray. And Sophie has research interests that are focused on better understanding of the solar source of space weather events in order to improve predictions of their impact on Earth. So very relevant, I think, to our discussion. After completing an MSc at University College London and a PhD in solar physics at Trinity College Dublin, she worked at the Met Office, UK's National Meteorological Service, and she collaborates with scientists, forecasters, policymakers, and end users to transition basic research to operational and space weather forecasting products. She's now a research fellow at the Trinity College Dublin and visiting researcher at Dublin Institute of Advanced Studies, and holds an Irish Research Council postdoctoral award, and is principal investigator of a European Office of Aerospace Research grant. So with that, I'd like to introduce Sophie, and thank you for agreeing to present today.
Thanks, Dan. It's been so interesting hearing all the discussions so far. It's very much just great to hear all the sort of the concepts of collaboration and open science and data. I think it's been a really, really great week. So yeah, I work in the area of space weather forecasting, really, and which is such a, as all of us really are, it's so interlinked, and so many of the solar and helio and earth science sides of things feeding those basic research topics into forecasting. And of course, it's becoming a more and more popular topic as we, switch our sort of our technological dependence higher and higher up. I think, we're really becoming a very technologically dependent society. I very much, as Dan said, it was really about research to operations that I focus on. So R2O is the classic acronym for that. Taking new science ideas in the area of space weather and then transitioning them into operations. So talking to forecasters, finding out their needs, and developing tools and products for them that they can use from our basic science ideas to provide guidance to a variety of users, whether it's aviation or spacecrafts or power grid operators, so many different types of users that are out there. And I'm very much focused on the solar side of things at the moment, so very much into solar eruption prediction. It's very much a starting point for your classic space weather forecast that you'll find. This is just a typical NOAA Space Weather Prediction Center forecast in the US. And you can see you have three letters, R, S, and G. And, R is standing for the radio blackouts, which have their solar source in solar flares, of bright flashes you see in extreme ultraviolet image there. You've got G, which is geomagnetic storms. These are from it can be everyday sort of space weather, high speed solar wind streams, but then the more extreme coronal mass ejections as well that can impact things like our power grids. And of course, the gorgeous northern lights as well. And then our solar radiation storms. So solar energetic particles, accelerated protons, electrons associated with these flare and CME events. So you have these solar sources that are very interlinked with the kinds of space weather forecasts that operational centers will provide. Now, in this talk, I'm not going to cover everything. I have my time limits, and my very much my focus has been for many years on solar flare prediction. So I'm going to talk a little bit about that today. It's also a really interesting topic to consider from a state-of-the-art point of view, because it's probably one of the oldest type of space weather forecasts that we have out there right now. You know, we've been forecasting this since the beginning for many decades now, and there are just so many flare forecasting methods out there available for operational use. So we very much reached a kind of a very timely point, I think, in our community where we need to take a step back and decide, you know, where are we, what is the state of the art, and how do we move forward? For those of you who aren't solar people, just a quick solar flare 101. When I say a flare, I mean an eruption of, you know, basically radiation across the entire electromagnetic spectrum. So it's not just that bright flash in the EEV, lovely Solar Dynamics Observatory image there. And we actually generally measure them in terms of their GOES spacecraft X-ray flux. So you can see those A, B, C, M, and X classes there in the X-ray flux. A, B's, and C's are generally kind of small in terms of radio blackouts and communication disruption. They will still, of course, do that. But from a space weather point of view, for forecasters, they really care about those M and those X class flares that will give the big disruptions. And of course, they're rarer events, so harder to predict than those A, B's, and C's. And I'd like to take you kind of on a story of how we create these forecasts, because I think, you know, the technique and the process that we follow is generic enough to really cover other different types of space weather forecasts as well. You know, we have to identify some sort of property that is related to the event type that you're trying to forecast. And it really starts at that point to get to that forecasting point at the end. For flares, we're quite lucky. It's a pretty easy option in terms of what property we're talking about, because we know that these sunspot regions on the sun, you can see them here with dark spots on the solar surface and white light on the left, and these black and white regions in the magnetogram there on the right. These regions of really strong magnetic field, we know that they're very much related to flaring. You know, we know that big regions that are quite what we call magnetically complex and they rapidly evolve are much, much more likely to flare than others. And you can see that you sort of, you know, I guess space weather forecasters will look at these images, they'll track the evolution of these regions. You can see this one at the top, although it looks quite big, actually doesn't do too much. If anything, if you look at its magnetic field, it kind of decays as it moves across the disk. But from a space weather forecasting perspective, it's that region there at the bottom, that small sunspot region there. You can see it's smaller and it gets bigger rapidly. This is over a few days in the sun. It emerges. So it's harboring more and more and more magnetic energy. And it's becoming how we define a magnetic complexity. That's your property. So as it becomes bigger and bigger, it's harboring more energy, it's more likely to flare. So we need to take that property and convert it into a forecast. And you can do many different things to characterize this concept of complexity. You know, it's a very, very much a generic definition. You can define it in many different ways. You know, in terms of a property or a parameter to use for forecasting, a lot of people will, you know, calculate various different measures from those data sets. You take the magnetogram, you might calculate the area of the region, or the total flux, or the total amount of helicity, or the current density, polarity inversion line characteristics. You can take loads of different measures, calculate what you want from that magnetogram, that first input data set, and that image of the active region or sunspot region. So, you know, that's kind of a classic scientific way of doing things. You might also use just a very simple classification scheme as well. This is something that's really, really popular in operations. And a classic example here on this slide is the Hale classification schemes. You've got alpha, beta, gamma, delta. So there's alpha, unipolar spots that are just a single polarity are just much, much, much less likely to flare than those intermixed polarities, black and white regions of gamma regions. And then you've got the big delta spots that are, the big, bad, ugly regions that are very, very likely to flare. So you take that characterization, this complexity measure, however way you want to do it, gives us a way to characterize, and then we convert it into a forecast. And this is what you would have seen on that SWPC forecast. This is another example of a more detailed forecast from the Met Office in the UK, where I used to work, of M and X class flares. So there's your radio blackout classifications, R1 to R2 for M, R3 to R5 for X class. And they actually forecast 4 days ahead. So they take that measure, they convert it into a probability. So in this case, if you look at this one here, that's an 80% chance of a flare occurring somewhere on the sun in the next 24 hours. And they do that for 4 days ahead. So we've got kind of two different things that will create lots of different types of forecasts for us in terms of solar flares. We've got that complexity measure, what property you want to pick. And then you also have the method you choose to convert to that probability. And that's where the mathematical modeling comes in. And this has evolved over the years, and we have been left with lots and lots of different techniques that we can use. The early days of flare forecasting very much focused on statistical methods based on historical flaring rates. So this is an example here, massive big table of numbers. What you're seeing is the Macintosh classification, which is being used, another classification scheme, and then lots of numbers of the number of flares that are associated with those particular active regions. So you use the average flare rates of different complexity classifications, and this is a Poisson statistics technique. So you assume a Poisson process and you calculate a probability. It's a very simple technique that's been standard in operations actually for many, many years. And operational forecasters like simple, quick, robust methods, and something that's easy to install, that's usable, that's going to be robust, that's testable, that's tried and tested methods. So Poisson is a very, very popular technique. And, over the years, of course, other techniques have popped up. We've obviously built up these data sets over solar cycles, more and more flare observations and complexity classifications. So big data, of course, makes you think machine learning, and that has become much, much more popular in recent years. We have seen people dabbling with various different techniques. Probably think of any of your favorite machine learning technique, and it has been tried on magnetic properties of active regions, logistic regression, random forests, support vector machines, neural networks. Lots of different techniques have been tried. So, we've moved from those statistics into machine learning. But the caveat here for flare forecasting and for many different areas of space weather forecasting is whatever mathematical model you're going to use, it's important to note that there's always a human forecaster in the loop. There's someone sitting on the space weather forecasting bench, observing those sunspots, looking at the outputs of those mathematical models. And they can edit those numbers as much as they want before they provide their guidance to their users. They don't quite trust the automated methods yet for flare forecasting, and for many other different things. They have their expertise that they can use to edit those numbers. Why don't they trust them? Well, really, there are almost too many flare forecasting techniques nowadays to choose from. For a long time, I think in our community, it has been really unclear which of the many available methods are the best to use. There's been an absolutely massive surge in the number of flare forecasting methods that have become available recently. And here's a plot version of that. So what you're seeing here on the left is the number of, what I say operational, I mean basically things that are available online. So probabilities that you can find in real time online, and forecasts that are available since 1992. And you can see there was only a few forecasting centers who were doing this up until around 2010. We had the launch of NASA's Solar Dynamics Observatory, which I find fascinating because you see this massive surge all of a sudden in the number of forecasts becoming available. We had suddenly really high resolution data from magnetograph, HMI, and of course everyone wanted to do some really cool new science with these, you know, beautiful data sets, and lots of machine learning techniques being used. And that's left us with a really flooded market in terms of flare forecasts. You know, usually it's great to have options, but I think in operations that's really not necessarily the case, because it can be difficult for forecasters to know which method should they be basing their guidance from. And that's even more apparent if you have a look to the right here at this plot of variance of the forecasts. So you get this huge spread in the probability values from method to method, whether you're using stats, machine learning, or whatever technique you're using. You know, you get this huge spread in values when there isn't an obvious massive complex region, or maybe no regions at all on the solar disk. So, you know, these low probabilities, not much of a spread there because there's nothing happening on the sun. Or if there's an absolutely massive region, you're going to get, you know, everybody kind of bumping up their numbers. But that bit in between, huge variance. So that, you know, that makes it confusing for the forecasters to know, you know, which one is right without a proper evaluation of all these methods in a consistent way. So we have a lot of parallel efforts in flare forecasting at the moment. And we as a community needed to take a step back and think, okay, well, out of all these parallel efforts, which one is the best? And we really needed to focus our efforts to figure out, well, what is the state of the art? Even though we've been forecasting for decades, we didn't really know where we were in terms of state of the art. And, you know, this is where the community efforts come in, because traditionally the flare forecasting community hasn't been that great with evaluation. You know, this is something that was really done by a lone scientist or a group of scientists in a research institute for their own research paper until very, very recently. You know, people would kind of just pick their favorite metric or maybe just copy whatever they'd seen been done in previous papers. And even if they did copy the metrics from previous papers, they couldn't be compared because different papers were focusing on different data sets, you know, over different time periods. I'm going to say the word different again, with different amounts of flares observed. So they weren't comparable. You know, you couldn't just compare the skill of a newly published forecast to what else was out there already. So we really didn't know where we were. And in terms of metrics, what I would call categorical metrics were being used. So, I mean, don't worry about this slide too much, but this is what I'm talking about. You convert your probability value, that percentage chance, to a yes or no forecast using a threshold. And then you have this lovely contingency table to allow you to calculate loads of different types of skill scores. So there's loads of options there in terms of metrics, but we weren't really comparing them very much. And we ended up talking to our weather forecasting colleagues, or terrestrial weather rather than space weather, who have been evaluating their forecast, you know, rainfall or wind speed or you know, loads of different weather phenomenon for many more decades than we have. And they really are experts in this field. They pointed out that we're actually losing a lot of information with the kinds of things that we were doing because we predict probabilistically, but then we convert to a yes or no forecast. And this actually came from the concept of an ideal forecast, of being able to tell a forecaster, yes, there's going to be a flare, or no, there's not going to be any flare today. You know, it's the holy grail of an all clear forecast, but the science for us just isn't there yet to be able to do that. And so, you know, we talked to our weather forecasting colleagues about, you know, what should we do? We chatted within the community, and we got the scientists together with the space weather forecast, the operational centers, to start to compare our forecasts in a consistent way. So we basically ran a series of community workshops to define some new standards for our field and create some proper operational forecasting comparisons for the very first time. It started, there was a workshop in Nagoya back in 2017, the International Flare Forecasting Comparison Team workshop. Literally science, flare experts, evaluation experts, space weather forecasters, all sitting around together in a room, deciding what to do and how to compare their metrics, their forecasts for the very first time. So we decided to compare those forecasts that I showed you before, you know, that 80% chance of a forecast of a flare happening on the sun. So what we call full disk daily forecasts. And we had to sort of think about, okay, so we know what we want to do. how do we do it? We had to define some metrics, a data set, a benchmark. And, you know, when we had to decide on metrics, operational people like me were keen to you know, move towards some weather forecasting evaluation tools, some probabilistic things. Some examples here are on your screen. And I'm going to mention these again later, which is why I'm going to explain them now. So on the top is what's called a relative operating characteristic curve, or a ROC plot. It's basically hit rates versus false alarm rates. So in an ideal world, your curve, you want to be in the top left of that plot there, where the hit rates outdo the false alarms. And you don't want to be anywhere near that no skill diagonal line. Now, ROC plots are conditioned on observations. So a good companion to them, you'll often find they're kind of shown together, is a reliability diagram, which is conditioned on the forecasts. Here, you've got basically your frequency of observations versus your forecast probability. So in this case, you're forecasting 20% chance, you observe 20% of the time. You want these to be equal. So this time your skill line is the diagonal line. And I like these kinds of evaluation tools because they're really visual. It's nice for a forecaster to just make a quick look at these plots and make a tangible link to a skill rather than, you know, a massive table of numbers. But saying that, you know, we didn't want to limit ourselves, so we calculated every kind of metric we could, and because I think we find that different forecasters will be interested in different types of skills for these forecasts. So the key with us was, you know, and it was being brought up yesterday as well, was to share our results openly, you know, publish the data sets openly, show the code that we've used, provide everything openly so that anyone could calculate any metric they'd like from our work. So that was the metrics. After deciding on metrics, we had to then decide on a data set. That one was much easier because we just had to pick a couple of year period where everyone had data for, you know, there was an overlapped period, because some forecasters are, you know, newer than others. And then a benchmark. And this, you know, took a little bit of time to define because some people don't even think about a benchmark. Others will just take an average over a data set. Excuse me. But averages aren't necessarily helpful for imbalanced sets. What we ended up doing was something called a rolling climatology. It's a piece of work that a weather forecasting evaluation expert worked with myself on a couple of years ago. We looked at the kind of the ultimate time period for a rolling kind of climatology for flares. We had to avoid variances in the solar cycle. We had to avoid persistence, which is the solar rotation rate. And we found this sort of sweet spot. It was about 120 days. And so you take that average over that period and calculate it for each of your different forecasts. And it was a really useful tool, not just because we'd done something like this before. It was just the fact that everyone agreed, let's take that as a benchmark. So for the first time in our community, we had something that was consistent to compare to. We had defined our metrics, we had defined a data set, and we had defined a benchmark for community use for comparison in the future after we finished this work. So putting all that together, we compared our forecasts. And this is, you know, showing the results of our hard work. And I know there's a lot of plots here, so I don't expect you to take it all in, lots of colors. There's basically 18 operational forecasts on this slide from all around the world, from all the different continents nearly, I think. And, you've got the Poisson techniques there. You've got some that are using Hale classifications or McIntosh classifications or helicity or, different magnetic properties. You've got some machine learning in there. And you've just got human forecasts as well, human expertise forecasts. So loads of different types of flare forecasts, and they're all being compared to this climatology. For the very first time. So it was really fascinating to just take all this in and see how we're all doing compared to each other after, writing all these papers separately for so many years. It was really, really a fantastic process to be part of. And, as I said, I'm not going to go through every single plot. Maybe just notice that, none of the rock plots are all in the top left. And none of the reliability diagrams, none of them are all lying perfectly along the diagonal. So actually what we found was none of them were really doing all that great. There wasn't one shining star in this data set. The machine learning wasn't doing amazingly better than the Poisson technique. In fact, we found that probably overall, it was the human forecaster that was doing the best, the ones that were using their expertise to monitor the sun. And they are sitting at the bench looking at these data sets all the time. It's really interesting. I showed you that Met-Office forecast earlier. They take usually the mathematical model for the first day and they might edit that. But for those day 2, day 3, day 4 forecasts, it's actually all their own expertise. They have a look at active regions coming back around the back of the sun or leaving the solar disk, and take all those kinds of features that they see into account to make up their own probabilities. So having someone with that level of expertise and having a human in the loop is actually, the one to beat in terms of flare forecasting. And this is really, really fascinating for us as scientists who have tried all these different techniques over the years to find that actually they're all very, very similar in terms of the results. They're not massively outperforming climatology. And, without this community effort and this collaboration, we wouldn't have realized where we are in terms of the state of the art. It was really, really fascinating stuff. And it highlighted to us the need to go back to the science. What do we need to do to improve upon this? We have all these different techniques that aren't doing very well. We particularly had to think about our data inputs as a starting point. All those forecasts I mentioned use magnetic field properties, which are really quite similar measures. They all start with the same magnetogram data, right? It's just that one magnetogram image. So that's really limiting your inputs. And remember that these are things that we've been publishing in literature for decades now. We see these same kinds of properties over and over again. And I think there's a part of the human brain that becomes a bit of an imagination limiter with this stuff as well, thinking of new things that we can throw into our models. So there's been some really interesting new efforts in the field I've noticed in recent years, trying to take a step forward and improve upon the state of the art. It's kind of really interesting because it's a perfect example of making sure that you work with the experts on these things. A lot of the machine learning techniques we had, it was just sort of people sort of throwing loads of, any fancy machine learning Python package they could get their hands on at these magnetic properties. And they weren't necessarily doing all that well. But we've seen people, working with real data scientists in the field to get this right and to do better than those benchmarks. I think NASA FDL is just a prime example of this. Working, getting your solar scientists working alongside the data scientists, thinking about, well, what is your input? What do you want to get out of this? A really interesting, I think, technique that's been very useful, I've been kind of following lately in the literature, is the better use of data or input data with deep learning. So you can see here, rather than properties, they throw images at the computer. So, you're removing that imagination limiter. We're not doing the same property over and over again. We're seeing what the computer comes up with in terms of the features in the images. And you'll also see in this slide, it's not just the magnetogram they're using, it's all the different wavelengths that you can get from Solar Dynamics Observatory. So it's information that the solar atmosphere gives us as well, which is really, really interesting because, we've known from science case studies for many years, there are many indicators in extreme ultraviolet light in the solar atmosphere that are related to flaring and solar eruptive activity, but it's not something we've really used for flare forecasts before. These are, all the different wavelengths from AIA on Solar Dynamics Observatory. So not just the magnetogram, but also looking at these bright active regions in the solar atmosphere, these sorts of S-shaped structures, the flux ropes and the changes and the evolutions of them can be really, really useful indicators. So yeah, it's fascinating stuff. I think we're making some really good strides to try and improve upon where we are in terms of the state of the art. But remember, I said to you before, operational forecasters like simple, robust, tried, tested techniques, right? So it's going to be a while before any of the science stuff is in any way operational. And it begs the question, what can we do in the meantime? And this is where we took a step even further back and we just went to the forecasters and said, okay, so what do you really want? We're always creating these probabilistic forecasts, but what would actually be useful for you every day? And the one thing they said to me was, what about warning rather than forecasting? we'd love a heads up if a region that maybe we can't see it by eye, but maybe some of those properties you have could tell us if there's something going on in that active region that we're not seeing in the shape or the structure of it. And we actually already have the data for that already. We have all those stats for our different techniques. This is just a plot that a student of mine mocked up recently. It's just simple histograms. You're literally just seeing total active region flux for different flare classifications, C, M, and X over, I think this is 2 solar cycles worth of data. And you see this shift in distribution, right? So you're seeing these X-class flares being associated with higher valued flux in active regions. And it's not new, exciting, massive science or anything. It's something we knew already. There's big, more complex regions being associated with those big classifications. But just doing simple histograms like this can give us a value for our forecasters. We can draw a line and we can create a threshold, a warning threshold. So, they might have like a little infographic, with their traffic light colors, and maybe the active region will flash red if the flux value will go over a certain value. So it's really, I think it's a different mindset working with different kinds of people in space weather. Us as academics, we want to do the really cool new exciting techniques and try to get some really complex understanding of the physics. But sometimes the forecasters just want something simple, and we probably already have it lurking in our data. It's just a question of creating a product, simple tool for them. And it also helps us in the other areas of solar eruption forecasting as well, because, I'm talking about flares. One thing that I haven't even, I really don't have time to talk about is the concept of CME onset. And I was thinking about, what are the hot topics for the next generation of scientists to work on over the next decade or so? And this is a really big hot topic, because if you remember my SWPC forecast all the way back at the beginning, there were probability values for the flares and for the SEPs, but there wasn't for the CMEs. Right now, we observe the CME and then we predict its arrival at Earth, but we don't predict when it might erupt from the sun. And that's a big, that's a really big topic. It's something that we need to start working on, I think, on the science side of things. And in the meantime, we can use these simple warning systems to help forecasters as well. So not just warnings for flares, but warnings for SEPs and for CMEs as well. Even a simple scatter plot like this can do the job in terms of defining some thresholds. This is just your total active region flux again versus CME speed this time. And the colors are telling you the size of the CME. So the yellow dots are big halo CMEs, so, that go across the full field of view of a coronagraph right at us towards the sun. So if you want to, warn a forecaster about an active region of those potentially a region that would erupt, that would give a big fast CME, you could then just use your stats and define those warning thresholds. So sometimes you do need to take that step back and think about what kinds of things that, your user, whether it's a scientist or a forecaster, wants. And sometimes, some of the answers are staring at you in the face, even though we have been so focused on the probabilities for some time. I think simple techniques like this can be really, really useful for the future while we get our act together on the science side of things. And there's one other technique that I think is just crucial, and it actually just got mentioned earlier, is ensemble modeling. I really like to highlight this technique because I think it's something that's going to be useful for not just flare forecasting, but for many fields, and it already has already. I mean, this has been around for decades now. It's such a super well-established technique. It's used in data science, of course. It's so well established in weather forecasting, just like data assimilation is. It's the standard for many operational models. And I think even, if the public are used to hearing the concept or seeing the concept of something, then it really is super well established. This is an example of an ensemble output for hurricane forecasts in Florida. So those different colored lines are different outputs of a weather model. So different weather models, it's called a multi-model ensemble, giving you different potential paths of the hurricanes. So really, really standard technique is this concept of a multi-model ensemble. And it has been, already just super, super useful in space weather forecasting in other fields. It's been widely used, for example, in the area of CME arrival time prediction. So, as I was saying, we don't do CME onset forecasting, but, once we observe the CME, we do predict its arrival at Earth. So you observe, you might measure the CME speed, its angular extent, its position, and then you input those parameters into a heliospheric propagation model like NLIL, for example, that NOAA Space Weather Prediction Center uses. And then it will give you a prediction of how long it'll take to travel out and arrive at Earth. But if you perturb those input parameters, you vary the position by a few degrees or by the speed by tens of kilometers per second, that'll give you a perturbed ensemble, because you're running that one single model multiple times. And what you end up is a spread of arrival times. So such a super, super useful thing for forecasters. It put error bars on something. I know Ryan mentioned that earlier. Error and uncertainty is just such a key thing, I think, for us moving forward in any area of space weather forecasting and the kinds of products we develop. Being able to say that a CME is predicted to arrive at midday plus or minus 5 hours is just so much more useful for a forecaster. And it's something we're absolutely terrible with in flare forecasting. You never see that 80% plus or minus 10%, you just see that 80% on its own. And we definitely need to do more of it. And I think ensembles are a great kind of step forward for that, actually. But I would say baby steps for us, because all those ensembles have been around for decades. And so flare forecasts, they've never been merged together before. We have never bothered trying ensembles for flare forecasting. So we decided to utilize that flooded market I showed you earlier, all those techniques that we have that are giving different probabilities, but none of them are all doing all that great. And it's not useful for the forecaster because they just have too many to choose from. So why not create an ensemble to give them one single input for their guidance? So create a multi-model ensemble for flare forecasting. So you have multiple different models that are producing different prediction probabilities, and combine them together in some way to produce one single output ensemble forecast. And you can combine them in many different ways. Linear combination is pretty popular with a weighting scheme. Actually, I find in weather forecasting, just as an equal weighted scheme is actually the most popular. Literally what's called an ensemble average. You're just literally taking an average of the data set. Super simple, sounds too simple, but it's insanely effective. It really does just provide one single output. It's actually kind of a standard if you ever look at operational sort of requirements for models to have ensemble averaging for models for weather forecasts. So, if it's doing so well for weather, we may as well try it for flare forecasting, right? And here we go back to our rock plots and reliability diagrams again. You've got 3 colors. And so the blue is the best automated forecast in this data set. I think it was a Poisson technique, but of course it's going to vary from data set to data set. But the best one overall in that data set, so an automated technique. The black color is the human edited technique. So this is something that's just, remember before I was telling you that, our benchmark, our best output right now is a human forecaster's expertise. So that's this is the human forecaster in black. And then we have the ensemble average in purple. And you can see it does really well. Just taking the simple ensemble average is improving upon all those, parallel, sort of similar, mediocre forecasts. Combine them all together gives you a better single output for a forecaster to use. You can see actually in this particular data set, the automated method, that blue one there, was tending towards the horizontal line, which is the line of climatology. So as I was saying, we're really not doing all that much better than climatology. So that ensemble averages is pulling that automated output to rival the human forecaster a little bit in that gray zone of skill there in the reliability diagram. So super simple technique, but really powerful. And I think it's really going to be a very useful technique for flare forecasts while we improve the science, we can use what we've already built up to create these sorts of ensembles to help for forecasting. Now, we did mess around with different linear combinations actually for this study a little bit. We found one that did beat the forecaster for the data set. It was a linear combination with a weighting scheme based on a particular evaluation metric. So this is something called the Breyer score. I won't go into details, but that's the cool thing about ensembles, is that you can weight it on whatever you want to. So you can choose the evaluation metric that suits you the best. And you can see here in this case, it does pretty well in the rock plots. We're still never really getting to that corner. We do have a good ways to go with science, but we're definitely improving upon what was there before. And interestingly, though, check this out on the reliability diagram. And this really shows you why it's good to look at different metrics. Don't just do one, look at different types, because you'll find different skills in these different tools. It ends up being along the diagonal, which is what you think you'd want, right? But you can see all these forecasts on the right-hand side of the diagonal are what we call over forecasting. So most of the sets before are over forecasting, but this new weighted ensemble in turquoise, there's a couple of data points there to the left of the diagonal, which means it is under forecasting. So it might be that a forecaster, even though this is the overall best ensemble output, might not pick it because they might not want under forecasting. They might not want to miss an extreme event, a rare X-class flare. And this is a really useful thing about ensembles, is because you can choose the weighting scheme based on end user needs. Does a user want to mitigate misses? So they want to mitigate false alarms. Choose the metric that suits the user the best. And it really is, again, highlighting the importance of figuring out what you want to do with these things. There's a really cool tool that's hosted by NASA Community Coordinated Modeling Center called the Flare Scoreboard. And this is, kind of just, I think it's called ISWA, so it's kind of like a GUI. You basically click on these active regions, and it's a nice visual way of seeing what different operational centers around the world are predicting. So you get, lots of different people who have agreed to produce and send their forecast to the scoreboard, but also underneath it, you can see underneath the white lines, you have those averages as well. So it's a good starting point for a forecaster. And if you're not into flare forecasts at all, of course, there are other scoreboards as well. There's SCPs, the CME arrival time prediction, and there's, of course, BSED prediction as well. And I believe there's lots of other in the pipeline. So do check out those scoreboards. I think it's a good way to get a sense of what we're doing in the community in terms of the forecasting sides of things. And if you want to learn a little bit more about ensembles as well, there is an ensemble working group, which is part of the International Space Weather Action Teams that I just want to highlight quickly before I finish talking. ISWAT is a really interesting COSPAR initiative where, if you go on the website, you'll basically see lots of different groups that are collaborating on various different topics related to space weather. It gives you a really good sense of kind of existing efforts that are happening around the world, and gives you a chance to, engage with them and start collaborating. Even, you see something that's missing, it's encouraged to create new teams to develop these things and advertise them internationally, so you get lots of different people working with you on it. And this ensemble team was interesting. It started off with a workshop back in 2019 in the Netherlands before the pandemic hit. We were lucky it was the later half of 2019. And we got lots of different scientists together with operational forecasters as well as a weather evaluation expert. And when I say lots of different scientists, I mean people from the different subdisciplines in space weather, sun-earth connections, so solar people, helio people, magnetosphere, ionosphere, geomagnetic, lots of different areas of expertise. And, we're all doing different things with different data sets, but actually we're all running ensembles. So we're doing actually very similar efforts. It was a fantastic way to compare what we're doing and share, share lessons and share codes. And it's funny when we're having conversations, we all had the same questions to the evaluation expert. Well, what metrics should we use for this? Or how many ensemble runs should we have? And we had so much in common. And it's really interesting getting people from subdisciplines together. I think it's really, really important in the general sort of sun-earth connection. Having worked on solar, heliosphere, thermospheric projects in the past, it's really interesting to see how different the ways people can work within the communities are, but we are actually doing really parallel efforts. Although we're working on similar techniques, we might use different terminology or different acronyms, but there's a lot of overlap there. And I really think communication is key. It is a bit of a messy space weather system. It's kind of illustrated by this diagram here in the terms of the connections of the different kind of people who are working on this area. And it's really very, very different how you would communicate your project results with other researchers in your field, whether they're other scientists in your field or other subdisciplines, co-developers who are not necessarily astro experts, forecasters, end users, in industry or government, the general public who might be interested in aurora forecasts. There's so many different people. So it's absolutely key to identify your users at the very start of your project. And, maybe they're fellow scientists on just a normal basic, case study research project, or maybe it's an R2O project. So you engage with forecasters in industry, excuse me, but knowing who your project is for from the outset is key to make sure you're developing the right thing. And that was, something that we've really learned from flare forecasting, talking to those forecasters, realizing we actually have all the data stuff for this warning system and we didn't even realize they needed it until we talked to them. And I know R2O can be a little bit of a different kind of process than, what's really done in standard basic research scientists compared to what maybe academics are used to. There's proper, development for codes in terms of version control and code standards and testing. Evaluation metrics are often really a new thing as well, integration into industry systems. So it can be a little bit complex. And just before I finish, I just want to highlight, this is an application usability level system that's developed to help you track progress of a space weather project and from its outset through different development phases. And particularly the paper has some really good best practices for communications and working with different types of users. And so you're interested in learning anything about R2O, this is a really good place to start. So that's it from me. I think flare forecasting has been a bit of a problem child since the beginnings of space weather forecasting, and I think it still is. We definitely would not have learned where we were in terms of the state of the art in the field without getting together as a community and collaborating on that evaluation. And it's really enabled us to learn, where we are and identify things that we need to do in terms of our data inputs and the techniques we use and the experts we work with to try and improve upon that state of the art. And I think there's some really cool new topics and things like CME onset forecasting there that are going to really pick up in the coming decades. So yeah, that's what I really would say to you. I think in terms of projects and lesson learned from the flare forecasting community, to really collaborate with people and just take that step to reflect and identify your user needs from your project outset rather than, plowing forward and reinventing the wheel all the time. So I really encourage you to do that and just see what's happening in in other fields as well. So if we didn't ask those data scientists and those weather scientists for help, I think we would probably still be doing the same things we were doing before. So I think we can really learn a lot from each other. And this is the great thing about this Jack Eddy Symposium is we're bringing loads of different subdisciplines together. So thanks very much for listening.
Thanks, Sophie. That was brilliant. Really great to hear how you've been able to move things forward by reaching out to other communities, and I think this is a great example and exactly the kind of thing that we are trying to do in this with this symposium. So Ryan, I imagine we have lots of questions in Slido, so maybe I'll turn it over to you.
Yeah, and thank you, Sophie. That was a brilliant talk, as Dan mentioned, and judging by the very lively discussion we have going on in Slido, as always, Sophie's talks are very generative. So we do have a lot of questions. I think I'll try and organize these in a somewhat coherent manner, and I'll start kind of high level. One question that was asked was, has the capability to forecast solar flares stagnated?
Yeah, I know. And I think it was for a while. I mean, even myself, what I would see, I would be looking at the latest papers that were published, and I'm like, oh, yet another flare forecasting paper, no. Because we were doing the same thing over and over again. We're using those magnetic properties, we're using the same stats techniques, and it was just on different data sets. We weren't really improving upon things. But I think there reached a point where we did that evaluation where people realized, okay, these are the things we need to change. So while I think that was the case maybe a few years ago, I think now we're making some really good new progress in the field. I love what's happening with using different data sets for sure. Rather than just the magnetic field, let's look at the solar atmosphere stuff. None of that kind of stuff has really been done in a proper evaluated way, compared to our benchmark. So I'm really keen to see how that goes and sees if it improves things. But I think we were stagnated, but I don't think we are anymore, which is good.
Thank you. Yes, and the ensembling approaches that you mentioned are really inspiring. It just knocked a lot of things loose for me. So there was a lot of questions around this idea of what features do we include in the model? What helps us improve the forecasting? I wanted to maybe start with the idea that the human-in-the-loop forecasters are kind of the gold standard. They're still doing the best, and that's because we're paying attention to a lot more than what we can possibly encode in these models, and that process is called featurization. So maybe, do you have an intuition about what these forecasters are paying attention to that we're not giving to the model yet?
Oh, that's a really interesting question, and it's funny because I think it's a hard question to answer, because I think different forecasters, even if you talk to them, look at different things. And there was an evaluation paper that I worked on years ago with someone from the Met Office, a weather forecaster, and we actually had a look at how the human forecasters did compared to that Poisson technique I talked about. And even you could see the difference between the skill level of a senior forecaster versus a junior forecaster, someone who's been doing it for years versus a really, really young person. And there's that kind of difference in the levels. And you can see that some would just look at the magnetic field, someone would look at the EUV. There wasn't one kind of thing that we could say, this guy did this or this girl did this and they made it better. It really definitely does vary from person to person. But I think the fact that they're monitoring all those different data types all at once, right? So they have these massive screens, they can see all the different wavelengths of SDO, they're looking at what's happening with all the different sunspot regions, rather than me just checking it once every couple of days. I was like, oh, that's a cool new sunspot group. They're looking at it all day, every day, because they are some 24-hour forecasting centers, and they have, these 12-hour shifts. So they can probably pick up changes in the structure in the atmosphere or the surface that we probably wouldn't see if we were just looking at it every so often. So there's probably, I think that's what probably we're getting when we're trying deep learning and stuff, is the computers picking up, structures that we're not necessarily seeing. Probably the fact that they're just staring at it all the time is helping it, Yeah. There's definitely not a metric out there to say this forecaster is seeing this thing, but it would be really cool if there was.
So to drill down a little bit into the more granular level of that, to the metrics that we do use, there are a number of questions about the features of the machine learning networks. Mm-hmm. So Nick asks, when the machine learning network is trained, which images or features does it find most useful? And I'll kind of add Ashna's question to that of, is there a relation between two of these really strong features of magnetic shear or twist of the active region in the flare eruption itself?
And yeah, that's an interesting question. I actually don't really know properly the answer to that without re-looking at some of those papers that I talked about, which I haven't looked for ages. I know for sure that people are doing different things, which is really interesting. So some people have tried full disk images. So they literally just put in the entire image, the full disk of the sun, into the machine learning algorithm. And that has provided different results. I think if you zoom in on the active region, the field of view of the active region, that might be a little bit better than doing the full disk, because you're kind of picking up more of the structure. It's the same thing if you ran an extrapolation procedure and you calculated, the twist and all the structures of the active region, rather than doing some big 2D thing and just calculating one property. I think definitely zooming in and getting that fine structure detail has been probably more useful. But again, this is just, one paper versus another. and they're not intercomparable because they haven't been part of that evaluation study. So I don't know for sure. So there's definitely features there. I think really it's going to be telling to find out when they do properly evaluate against what we have already. And until that point, it's not really totally certain. I can't remember if there was another part of that question.
Yeah, no, I think that focuses as well to the next question about the different machine learning models. Most of these papers that I'm aware of do have some kind of visual about what is most important, the importance of that feature to the model. And I don't know if there's a great kind of meta study, or maybe Sophie, you can speak to whether there's a meta study.
Oh yeah, in terms of the different properties, that's been looked at a couple of times. There's Monica Bober did a really interesting paper where she looked at sort of ranking of what were the best magnetic properties to use. I think she used a support vector machine. I can't totally remember what her paper was. But she found, I can't remember what point she found it at, but there was a point where just, if you kept adding, tens of properties, it wasn't helpful. There's probably only a top 3 or 5 or something. And once you get to that point, there's just no point adding more properties. And you do see time and time again, there's a European project called Flarecast that did something similar. They had they did try, basically look through the entire literature. And, I think there was over 100 properties that they tried. And there were just a few that actually ended up being useful. And they usually tend to be the same ones over and over again. I think magnetic flux, magnetic helicity, I think current density comes up. I can't remember for sure. I can look it up and put it in Slack later if people are interested in looking at the papers. But yeah, it's funny. They're all really, at the end of the day, I was sort of saying there's similar measures. So you get to a point where just the machine learning algorithm doesn't need 20 properties. It probably only needs a few for it to get the best it can out of that limited data set.
Thanks, Sophie. So Sophie is kind of unique in that she has a wealth of knowledge, not only in the scientific domain, but also in the applied, the operational component of this. So I want to make sure we take advantage of that. There's a couple of questions about how these flare forecasts are used, where they have impact. And so just very generally, Abhay asks, and Abhay, I hope I'm pronouncing your name correctly, how is the forecast used? As it is the communication satellite track for I guess, are they used for things like changing satellite communications trajectories? Okay. What other impacts do they have operationally?
Yeah, this is a really interesting question, actually, because it comes back to the concept of users, and it's an interesting one. I think a lot of people think, if you look at a SWPC forecast, maybe some power grid operators or some spacecraft operators who are quite knowledgeable about solar physics and stuff will look at it. But at the end of the day, usually what will happen is that you have tailored guidance for every different kind of user. I know in the Met Office, they have special pages for aviation, for power grid, and they're all very, very, very different things. Some aviation users only want traffic light systems, so they won't even see those probability values. They just want a red warning, and that's kind of comes back to my warning system. They just want to know, is there going to be a flare or not, or is there going to be something they should look out for? So it's very much tailored to the user. And even for flares, obviously you're talking about radio blackouts, so it's very much communications, aviation, military, radio traffic control, anybody, ham radio operators, the satellite communications, GPS disruptions. So there's lots of different industries involved, but it really definitely totally depends on the particular company. It will vary from person to person. And generally you'll find that the probabilities more than anything, so what we're producing as scientists, that mathematical model that's giving that percentage chance, will only usually really be seen by the forecaster. So for us as scientists, our user is the operational forecasters, and then their users are the companies. So there are, of course, exceptions to this. There's lots of different areas of space weather forecasting where your users will be the end users. But for flares, generally, it's that chain. So that, I think in the AUL paper, they call it the broker. So the operational forecaster is the broker in between the scientist and the end user. So yeah, often they won't even see probabilities. There'll be something even more simpler, or it'll literally be a phone call. An end user will call up and say, is there something going on I should be aware of? So they won't even see the numbers or the pretty plots.
Thank you. So we're going to run short on time, but I do want to ask one more question on that line is how do how have you seen it be successful that we step out of our kind of scientific silo and understand what do these people that I'm working with actually need? You mentioned during your talk about the features that people are interested in may already be available. We're just not providing them.
Yeah.
How do we create that communication? How do we talk with the users? That's
a great question, because it is hard. I think I was lucky in that I worked with these people every day when I worked in operational forecasting. So I had those contacts already. And maybe as a scientist who's never been to a meeting with these sorts of people, it can be hard to I think, conferences, something like the Space Weather Workshop, or in the EU, there's the European Space Weather Week. And that's when you get a lot of people from different subdisciplines together, and you'll get, satellite operators, you'll get the operational forecasters together to chat about these kinds of things. So I think those kinds of meetings where you have that sort of space weather link rather than, a really specific solar meeting is probably the best place to chat to people. Of course, I know these things are virtual these days, but I think we're slowly getting there back to normality a little bit. But yeah, I think, I think you'd be, absolutely welcome to, I'm sure the operational forecasters, a lot of these centers have scientists working in these centers. It's their job to talk to the forecasters. So I think getting in touch with the scientists at those centers are probably a really good stepping point. Just, talking to them, reaching out, finding what kinds of science projects that they're working on at the moment. And they'll then be able to translate all that math stuff to the forecaster.
Excellent. Dan, I will hand it back to you and thank Sophie again for a really excellent talk. Some of the questions we didn't get to, I'll put into Slack. And
sure, I'll answer them later on. Yeah, perfect.
Thank you very much, Sophie.
Thanks.
Great, thanks Ryan and Sophie. Okay, so we'll move on to our next speaker. Our next speaker is Dr. Stergios Misios. And Stergios is a Marie Sklodowska-Curie Fellow at the National Observatory of Athens in Greece. Previously worked at the University of Oxford in the UK, the University of Aarhus in Denmark, and the Aristotle University of Thessaloniki in Greece. He holds a PhD from the Max Planck Institute of Meteorology in Germany. His work helps to articulate the role of different forcing in the climate system by blending modeling and observation. So welcome, Stergios, and looking forward to your talk.
Thank you, Joanna. Thank you very much for your kind introduction. And I have to thank also the organizers for inviting me to give this talk, which is basically, I would like to go through the historical perspective, so to see how our understanding, how our theory and the tools have been evolved over time in order to address this, as the symposium says, the cross-disciplinary topic of solar climate influences. So essentially, I will deal more or less about the climate, the effects of different facets of the solar variability on climate, and how we think that affects on different on regional or global scales. So let me. Okay, so I could help myself by starting going back to actually the paper, this famous paper by Jack Eddy, the minimum paper, which was published back in '76. And I didn't know, I mean, I have read it before, but it's 15 pages length, which is something amazing for the current subject of a science paper or so. And this is, I tried to track actually the citation history of that particular paper, which to me sounds that it has been perceived in the beginning with some modest reactions, some skepticism perhaps, but later on you see this boom in the 90s, in the 2000, early 2000, you see this boom on the citation times, which seems that, which says actually that the interest of the community of different people working and scientists working in the field has been increased. Well, also, I think Gavin Smith said about the sociological impact of solar cycle, and clearly here you see, so it's just a Google search on solar cycle, you see clearly a pattern that emerges in the 11-year solar cycle variability. Of course, it's related to the to the hype in the news about the possible effects of prolonged solar minimum that happened in 2009 and 2010. And since then, while people don't very care or are interested on, on typing and searching about effects of solar cycle. Well, this is a short and clear bias to my interest, introduction of and the timeline of the history of sun-climate links. I should start with very much realization that actually the sunspot exhibit a periodic variation of 11 years. You can imagine how much excitement this observation by Schwabe has sparked to the people back then. There is a full list of different studies that are trying to relate solar effects with the weather, essentially. Moving forward to 1976, the famous Maunder minimum paper. In 1978, the Scientific Committee on Solar Terrestrial Physics was established as COSTEP that endorses multidisciplinary research on different aspects of solar, climate, space, weather topics. In the 90s, in the 80s, I think at least, Ken Labitsky and Harry Van Loon was very influential on striving and driving actually research on solar and climate relationship, and the famous connection and relationship and dependence of the solar cycle forcing and the quasi-biennial oscillation. This is an oscillation in the stratosphere, so between 30 kilometers, 20 kilometers, and 50 kilometers, which seems to be important on the effects on the stratosphere. In the 90s, Jo Haig and in her papers in Nature and in the Science argued that, it's important also the stratosphere that can propagate signals down to the surface, and also has the influence also the tropospheric variability. In 2001, I will stay on the very clear relationship between the solar variability and the North Atlantic oscillation, and this is a very important topic that always, still attracts a lot of attention in the literature. The Hepa Solaris group of different people, let's say, was established. From 2003 to 2020, we were very benefited to quantify the precise and reduce the uncertainty in the spectral irradiances, which play important role in the stratosphere, in the upper atmosphere in general. In 2009, and clearly it's related to the Maunder minimum paper, it's the Mans paper which shows the difference in climate between the medieval climate anomaly and the Littlest Ice Age, and how the spatial patterns of that. In 2009, and I will talk about that later, it's about the cloud experiment at CERN. Going back more or less to my interest, and it's about the effects on regional scales, particularly in the tropical Pacific. In 2009, there was a Mill paper in Science suggesting that there is a tangible effect of solar cycle on it. 2012, the Miyake paper on cosmic ray events we had before about the effects of solar flares, and this is a clear effect of a gigantic solar flare on carbon-14 records. In 2013 was a solar model in the comparison project, so it was one of the most comprehensive study of IPCC type climate models to see how well they represent, let's say, solar cycles and what the uncertainties and how we can improve actually the climate models in respect to the solar climate links. And the Presto is the predictability of variable solar terrestrial coupling, endorsed by COSTEP. And now we're talking about predictability by blending different different modeling, different measuring things, and very and data analysis. And one thing is to communicate, and this has been mentioned already in previous talks, that we have to talk scientists from different disciplines have to talk to each other, let's say, in order to improve and set the questions and improve the tools to address them. The pillar one is the sun and the interplanetary space, geospace. The pillar two is space weather and the Earth's atmosphere, and more to my expertise is the solar activity and how this translates and how this influences the climate, both on on fast time scales, for instance, a solar flare time scale, or on decade time scales, or even on centennial time scales if you are referring to prolonged solar minimum. You have seen this figure before, so it tries to encapsulate the different mechanisms we believe the solar activity influence the climate. First to mention is the galactic cosmic rays and the effects in the ionization and in the atmosphere, and this is related also to the perhaps on the formation of the clouds. And another mechanism that relates also to the galactic cosmic rays is through the atmospheric electricity. I will speak about that a bit later. The other avenue is the integral of the solar irradiance. We know that while between solar minimum and solar maximum, there is 1 watt per square meter increase in the total solar irradiance. And this, I mean, if you want to translate that, it's the global mean temperature response is small. But in the UV, depending on the spectrum, actually on the wavelength you are looking, you can detect changes between solar maximum and solar minimum up to 6%, 10%, if you go to extreme UV, even higher. And this has a very important role to play in the stratosphere. And of course, besides the radiance, the radiation component of solar variability is also the particulate component. Protons, fast protons that penetrate in the high latitudes in the stratosphere and influence the chemistry in the upper atmosphere, essentially destroy ozone, and this may have also affect the circulation in the stratosphere, and through which these two coupling between the chemistry and the dynamics, this signal can be amplified and affects the stratosphere and further down in the troposphere. Okay, so I would like to address why it has been viewed with this topic has been viewed with some skepticism. Well, in principle, skepticism is very the science itself, by definition, is based on skepticism and by try and error. What are the observed impacts and how and what climate models tell about that, and how we can explain the physical, essentially, mechanism behind these detecting signals. Well, I guess common pitfalls could be bold claims in the sense that we have this variation and explain the full range of temperature response that has been observed over the 20th century. So another thing is what I call it personal bias. So for instance, if you have some ideas about global warming and whether the man-made greenhouse gas don't play a role on that, so you can pick up particular relationships and explain, let's say, the observed global temperature increase to anything else but the true reason, which is the increasing in the greenhouse gases. Mistreatment of significance, assumption of stationarity. So the connection, I mean, you can think, for instance, that there is a time period that the relationship and holds strong, but of course the solar cycle is not the only force or external forces to the climate. For instance, I mean, in a period where a strong volcanic eruption may happen, you could expect, let's say, that this relationship is not valid any longer. And of course, we are about to understand and analyze a very short period, a very short data of quality control data. Of course, this is not actually a shortcoming to this particular field, but many other fields suffer from the same issues. Just an example, I'm taking this meta-analysis of many different papers in medicine, and the message is actually that it's more likely many of these studies to be a false positive, meaning that we detect something in the case when there is no actually relationship. And to go, I want to move forward, let's say, to explain why it's happening that. At least in the medical part, but applies also to many other fields. Bold claims on astrometeorology. So I will stay actually with a very famous paper from Herschel that related to the protract solar minimum to the prices of wheat in the London market, and this is something that it has been shown later that it's not actually it's not robust, and statistics is not well defined. You would expect that back then, because people had a limited number of observations and poor understanding what actually is happening and how actually the solar cycle affects climate. Still today, because I guess people from a personal bias, try to relate some of the issues of the solar variability to the global warming. And just, very recently, in 2019, there was a paper in Science Communication trying to relate, let's say, the distance between the sun and the Earth to explain the global warming, which of course is not. It suffered by many shortcomings, but still you could ask, does the solar variability plays any role to the observed global warming? And of course, you can test that, and this is the great help and advance from the climate models. You can have a climate model or a collection of a climate model or an ensemble, as we had before, of different models to test this question. And the beauty of the models is that you can specify different forcing. So you can think of, okay, let's see what's happening if you just specify the greenhouse gases, how much the temperature is affected by specifying the observed natural forcing. And when I'm saying natural forcing is the volcanic forcing and the solar cycle forcing as well. And you see here that, when you have all forcings together, the semi-ensemble mean, global mean temperature variations trace very well the observed signal. You can find, of course, some discrepancies, but in principle, let's say that you can reproduce, let's say, the warming trends to high degree. But when you repeat this game by specifying only the natural forcing, so volcanoes and solar variability, you see that you won't expect, let's say, to have this warming trend. Rather, I would say stable, or if anything, could be. And the stronger effect, of course, these dips in the simulation is the effect of volcanoes. As I said before, the solar cycle, the variation of the total solar irradiance between solar minimum and solar maximum is about 1 watt per square meter. And the very detailed recent analysis of Amdur et al. Suggests a sensitivity on the 0.05 K between solar minimum and solar maximum, really small one, let's say, and of course, but still, if you see here, there are arguments that perhaps not over the entire record over the 20th century, but over, let's say, over a decade, well, in the recent years, there was a slowdown. So you see here over this period, particularly between 2000 and 2010, there was a kind of reduction of the increasing rate of temperature, and there are actually studies suggesting that the solar cycle may have an impact and may has played some role on this reduction in a global perspective, of course. Well, I mean, as I said before, it's safe to say no, that at least the irradiance doesn't explain the warming trend. What about in the past? As I said before, the beauty of the model is that we can isolate different forcings, and this is an analysis we carried out using the last millennium simulations from 1850 to the present, where they did an ensemble of simulations, because even well, with a single simulation, it's very difficult to extract the solar component. It's hidden in the noise. And you see here, if you filter the time series, that the global mean temperature fluctuates in phase with the filtered, with centennial total solar irradiance. And interestingly enough, the coldest period in this particular simulation it's found to be coincident with the Maunder minimum. So, but still is very weak compared to the observations, and you need, as many other studies suggest, the impact of volcanic eruptions that happened about that time. Well, in the greenhouse gas only simulations, you see this steep increase after 19th century, which is solely attributed to greenhouse gases. Okay, well, perhaps could have an influence in the future, and this is what I said before in the early study about in the last solar minimum, where it was a very protracted solar minimum, whether a similar minimum or a grand solar minimum in the future could have any influence on the global warming trend. And you can devise experiments like that. So repeat the solar cycle and dip and reduce the total solar radiance, and then go back to a normal solar cycle, and you see that you can simulate the effects, which is very small, and of course it doesn't stop the global warming. Perhaps in regional scales could have some significant change, and could buy some time, let's say, because the spatial patterns at the surface are not uniform, and there are good reasons to believe that the solar cycle signature is stronger in the high latitudes. So in high latitudes could reduce, this particular study suggests, up to 40%, let's say, the projected warming by greenhouse gases. Another issue, another pitfall I mentioned earlier is the posteriori selection of limited data. And this is, I think this is a very well, I mean, in truth, I think it is a paper from 1999 where it shows almost an incredible correlation between the global mean surface temperature, you can't say what is what, and the length of the solar cycle. But I think this study has been driven more by political reasons in order, let's say, to explain, to find other mechanisms, but any other mechanism but the greenhouse gas effect. And I mean, if you scrutinize this relationship and you extend the record, not over a particular window, but over the to include many centuries, where we have observations with sunspots, you see that there is no actually correlation between the length of the solar cycle and the global warming, global mean temperature variation. So clearly this mechanism, well, it doesn't hold, and this study has been actually biased by limited data and I guess personal bias. Well, perhaps another study which relates to galactic cosmic rays to clouds. So again, if you see over a particular window, you may say about a nice correlation, but doesn't seem this relationship to hold over the whole period and breaks in the later part of the record. Well, I mean, I guess this is again an issue of a posteriori selection of data. So looking on different correlations, I think sooner or later you will find a relationship. There is no priori reason to believe why, or a mechanism to think why galactic cosmic rays could affect particularly the low clouds, not the high clouds, for instance. And it's just a matter that, well, I mean, you feed this theory fits, you find a strong correlation, you try to build up a theory from that. Well, in any case, this is not new actually. It has been argued about that and speculated even by Dickinson back in 1975. So where he thought that maybe the cosmic rays could affect, I mean, we know it affects atmospheric ionization, and through which could affect the aerosol formation and thus the cloud properties. We know this mechanism principle works under certain conditions, and we know, for instance, we have been using the GAD for years to trace, let's say, particles in a cloud chamber. And well, it's possible, and let's say that ion pairs, atmospheric ions, could provide another mechanism to produce aerosols, and this aerosol eventually will grow. It's not straightforward. It's not easy. Let's say the ions could produce some very small, tiny particles. That doesn't necessarily mean that these particles will grow to that size that could work as a cloud condensation nuclei to form clouds. But nevertheless, this mechanism was the driving force for the cloud experiment at CERN. So actually exploiting the particle beams from the accelerators from at CERN as a source of ionization beams in such a huge cloud chamber in order to study this mechanism. And it seems, and you see here, for instance, that the nucleation rate under particular conditions, but nevertheless, let's say that it seems that ions in the atmosphere could facilitate, let's say, the production of aerosols in an environment of low sulfuric acid. So this is the specific requirements in order to have this twofold increase in nucleation rates. So this means that perhaps this mechanism might be stronger, let's say, less polluted environments, or in the past, prior to the industrial, let's say, era. Another thing about galactic cosmic rays is that we know as they use the ionize the atmosphere, it might perturb, let's say, the electric properties of the Earth. So the Earth, you can think it as a capacitor, has resistance, and this can these properties can be modulated by the galactic cosmic rays. And it has been suggested, let's say, that may also influence some properties near the clouds. So there is a nice, let's say, study from Harrison et al. Where they found a nice relation between the atmospheric electricity and the cloud base height. So this is a topic, let's say, of interdisciplinary research, I have to say. So this is a European cost action electronet, where they try to study the different aspects of atmospheric electricity even on biological mechanisms. And there has been also a network of measuring atmospheric properties, and this is myself actually installing one of those instruments high up in the mountain, let's say, in order to study the variability of atmospheric electricity. Okay, we talked about before, by Sophie, by solar proton events, and this is another extreme. So we're talking about extreme solar proton events, where can be detected in tree rings. So when a solar proton event and associated reduce actually the amount of galactic cosmic rays that penetrate into the Earth's atmosphere, and this has an effect of the production of cosmogenic nuclides like the carbon-14, which fastly oxidize to make a carbon to be absorbed by the tree, and you can detect actually these fast peaks, these abrupt peaks in the carbon-14 concentration in the past. So in the past, I mean, there is a lot of research in that, and in the last millennium, up to now, we had until recently we had two candidates for extreme solar proton events, but a recent reconstruction of carbon-14 extending the last 1,000 years has identified two more events that could fall to that category of extreme solar proton events. And of course, this question has, I mean, a burning question is how frequent these events might happen. And perhaps, I mean, the recent findings suggest that might be more frequent than we thought in the past. And of course, what will be the effect, not only, let's say, in space assets, but on climate. And we're doing research on that. And we see that mostly it depends on the season when such an event might take place, might occur. It's a completely different story. For instance, if you have, if the solar proton event happens in summertime, as it has been suggested for the 775, which is the strongest event ever observed, or close to winter time, because close to winter time, let's say, this has a significant effect in the chemistry, in the ozone in particular, and this perturbs, let's say, the thermal balance in the stratosphere, and through the interaction with the dynamics, this may have an impact down to the surface. So it clearly depends on the season of this event. It's not, you know, it will happen. It will have an effect anytime. Going back now, I mean, till now I talked about effects of galactic cosmic rays, effects on solar particles, and now let's move to some correlations between atmospheric variables. In this particular is the temperature, or is the temperature in the stratosphere in particular locations, to the total solar irradiance. And as I said before, Karen Labitsky had, she was famous, I think, by writing papers with correlations, and she didn't present any statistical significance, any test about that. But still, perhaps you didn't need that because, well, when you classify, she did some data treatment and classification according, as I said before, to the phase of the quasi-binary oscillation, this circulation in the stratosphere. You see a very clear relationship between the temperature in this particular location and the solar cycle, which perhaps again may suffer by the limited data she had back then. I have to mention that climate models are have very difficult time to reproduce this relationship, and I mean, perhaps there are good reasons that the physics in the climate models is not mature enough, let's say, to have this this relationship, let's say, simulated. But clearly, we know essentially that the spectral irradiances in the UV and this interaction between UV variability and in the chemistry in the stratosphere does have a tangible effect on the atmosphere, and we expect, let's say, to have we expect a warmer stratosphere in a solar maximum between this interaction. This provides an amplification mechanism in the stratosphere, and you see here, for instance, from this reanalysis that the upper part of the stratosphere at about 1 hectopascal, so 50 kilometers way up in the atmosphere, it's much stronger. The warming there, it's much stronger than in the tropical stratosphere. Well, again, perhaps we are facing some, we have difficulties in detecting solar signals in a robust way. Particularly, perhaps the shortness of the observations may hamper, let's say, our detection here. Although it's significant, may signals down there contaminated by other forcing, particularly the two recent volcanic eruptions from 1979 happened close to the solar maximum. So this could have an effect, let's say, on the regression coefficients we get there. The same for ozone may suffer from the same shortcomings. But nevertheless, let's say, well, there is a theoretical background behind that. So if you, let's say, induce some, you can do it in a very mechanics way. So you can have a climate model and let's say induce some temperature variations in the upper stratosphere, and you can actually replicate that mechanism. So if you have a solar heating, excessive solar heating, let's say, in the upper stratosphere, you perturb, let's say, the latitudinal distribution of the temperature, and this induce some westerly anomalies, which over time, let's say, strengthen and go down, move poleward and downward. And this is something that we observe, and we are able to replicate with very mechanistic models. And if you have such perturbation, let's say, in the stratosphere, because of the stratosphere-troposphere coupling, we know that the variation in the stratosphere affect the climate, particularly in the winter time. And there are suggestions that actually the solar cycle may alter major modes of tropospheric variability, like the North Atlantic Oscillation. Which is something, which is a beast actually that lies here in the Northern Atlantic. Well, the interesting part is that this this signal seems to keep and stay significant, let's say, not only over the observed periods, but over where we have quality controlled observations. But if you extend back to 7050, where you have 24 solar cycles, so increase the sample of the sample size considerably, still you get that positive correlation between the positive relationship between the solar cycle and the North Atlantic Oscillation. We said about climate models, and now we have different families of climate models, like where you have specified, I mean, in order to simulate the effects of the solar cycle, the radius part of the solar cycle, you need essentially two components. You need, let's say, a variable spectral, a variable UV component and the ozone response. And you can do that either by specifying, so just put into the model actually the ozone response, or you can internally simulate it with a climate model. So there are different families of climate models. And this is an analysis we did with the SIM5 models. The SIM5 models are those models who are carry on simulations for the IPCC reports, and you see that you can find that the upper stratosphere seems to you get, let's say, significant signal in the upper stratosphere, significant warming, although there are, of course, uncertainties and differences between the model. So in principle, when you average, this is what Sophie said about the ensemble mean. So when you average over all different models, you get the multimodal mean, and you can compare with the observations, and you can infer, let's say, how well the model, the ensemble mean, let's say, replicates and reproduces the observed signal. And if there are discrepancies and differences, is there any particular reason, let's say, to that could explain these differences? And we think that, I mean, at least for the lower part of the stratosphere, while the dynamical response, this is an indirect response to the solar cycle, is not very well reproduced in the climate models. And the same thing also happens for the window time response. So the dynamics, the circulation in the stratosphere, although the sign is correct, so you get these westerlies that move polygon downward over time. The amplitude, if you compare to the observations, is way too weak. And of course, when you have a very weak response, a very weak perturbation in the stratosphere, you wouldn't expect, let's say, something spectacular to happen in the troposphere and the surface. So it's not surprising, actually, that this mechanism between the stratosphere, troposphere, and the North Atlantic Oscillation is not very well reproduced in this family of the models. So we think that particular reasons could explain these discrepancies. For instance, the models do not capture very well the dynamics of the stratosphere. And perhaps this could all have, let's say, an effect of how well the signal in the stratosphere and the troposphere is simulated by this family of the models. Another thought could be that perhaps some other key mechanisms are missing. And there is a suggestion, for instance, that, well, if you add the particles, particle precipitation, which essentially have the same effect, let's say, in the chemistry, could, let's say, this amplify the response of the solar cycle and could get a better results, let's say, and improved comparison with the observations. At the other side, could be, I mean, there is a suggestion that just these relationships we are inferring by statistical tools, essentially, like multiple regression analysis, it's just a fluke. It's just a fluke of the sort of observations. And there has been suggested, for instance, that well, the models, I mean, this is a simulation where the solar cycle, where the model has been forced with the solar cycle, but equally the model is able to reproduce a same signature to the solar cycle. Even we know beforehand that particular simulations have not carried with a solar cycle forcing. So could be one possibility could be that well, what we're getting actually, it suffers from the shortness of the observation. It's not a real signal. But still, the knowledge of the solar cycle seems to improve, let's say, the seasonal prediction. And this is a study from Danson and al., where they were able to predict, let's say, with high correlation, the North Atlantic Oscillation, the index of NAO, 2 years ahead, and they attributed this improved prediction into two components. Basically, the temperatures in the Pacific, and secondly, the polar vortex strength. And they saw actually that the polar vortex strength is closely related, is improved by specifying a varying solar cycle forcing on that. And you see that how well, let's say, the strength of the polar vortex follows the solar irradiance. Another topic actually that I'm working on is the possible effect, the purported effect of the solar cycle on the Pacific, and this has attracted a lot of attention lately, where and this started by this work by Van Loon et al., where they composited years belonging to the solar maximum versus climatology, and they saw that they were able to detect a very strong cooling over the Pacific, which resembles the El Nino oscillation. The El Nino oscillation is the dominant feature of variability in the temperatures in the tropical Pacific. And with the climate modeling, they were able also to replicate this result. But I think it depends on how you treat actually the observations, because if you repeat the same task, but this time by regressing, not compositing, regressing to temperature time series onto the solar cycle, what you get actually is a warming, not a cooling. So it's quite opposite to what they suggested. And again, the climate models seems to suggest that in fact the effect of the solar cycle is warming, a positive anomaly in the Pacific. And as I said before, let's say you see how much stronger the signal and how much the imprint, the signature of the solar cycle in the high latitudes is amplified. This has, let's say, a consequence to to other modes of variability or to the work circulation, and there are we're working on that and to understand whether the solar cycle could be a source of predictability, let's say, in the Pacific. Well, to sum up, we talked about effects of the solar variability on climate, either by modulating the intensity of galactic cosmic rays, or by solar proton events, or by radiation variability, and how these changes through different mechanisms are amplified, and we think that contribute to the surface and to the surface climate and atmospheric variability. I think it's getting clear that the climate models and the benefit of climate models is a game changer in the topic. And this is just a kind of perspective how the climate models have been evolved over time to simulate more physics, more processes, and consider more forcing related to the solar cycle. So earlier back in time, let's say, most of the models had included variations in UV and total solar irradiance, and the ozone was prescribed. In the later versions of the models, and as more processes and we are more capable of including more of having supercomputers, let's say, we can now simulate effects of solar proton events to have interactive chemistry. And even extend, let's say, the upper limit of the models way higher than in the mesosphere, and include, let's say, processes in the thermosphere and so on. This is something I could just keep for facilitating the discussion. That's from my side, essentially.
Thanks, Stergios. That was great. Really nice historical view there, and I think very honest view in terms of where people have maybe overclaimed the impact of the solar on climate. But I also think that we should. I mean, maybe the conversation has been steered too much in our study of the solar impacts on the atmosphere by this competition between whether or not it was the solar or greenhouse gases. And I think that now we should sort of move away from that and just try and understand the processes. I am fascinated by the potential that at least over this sort of 5-year timescale, say, where we're really trying to push this prediction window out, whether there is an important role for understanding solar processes. So anyway, thanks for that, and I'll turn it over to Ryan for the Q&A.
Thanks, Dan, and thanks, Sergios. That was a really engaging talk, and we've had a lot of discussion in the Slido that I'd like to get to. So maybe I'll start high level, and this is something that I was curious about. Just anytime the word climate is used, it sometimes can be met with contention, or that it comes with a lot of kind of prior beliefs or biases even. How do you work constructively in what can be a contentious environment?
For let's say to how to describe, let's say, climate in the audience, or what?
Yeah. So how do you do science in a environment where people could have very strong and differing opinions?
Right. Okay. Well, the thing is, as Dan said, that well, I guess there is no question about if there is no truly scientific question whether there is a kind of if the solar cycle, let's say, or the solar variability has any influence on climate, in particular whether it explains, let's say, the temperature trends. I think this is we have moved beyond that. It's more it's the question whether to understand the physics and whether actually the solar cycle could be used, let's say, to understand how like modes of variability, or like the Walker circulation, for instance, could respond to external forcing in order to help us understand how the very same mode of variability respond to other type of forcings, like even, let's say, even the greenhouse gas forcing.
Thank you. So something Dan asked, how might anthropogenic climate change be modulating the response of the atmosphere to solar variability?
Right. I'm not sure. Well, I'm not sure if this has been addressed actually. I think well, I mean, I can't provide any answer to that, but I guess might be related. I mean, perhaps maybe in the stratosphere, for instance, where we expect some parts of the upwelling, this large-scale brew-up circulation, let's say, to slow down in the in future climate. Let's say this could have an effect, let's say, on how the can modulate the effects, the signature of the solar cycle on in the upper stratosphere. But I'm not sure if it will play any. I can't give any definite answer for that, but I'm not sure if it can modulate significantly signals in the at the surface or lower down in the atmosphere.
Thank you. Yeah, sometimes the best questions are the ones we don't yet have answers to. Lika, do you have do you want to follow on that thread?
Don't know if it's exactly the same thread, but this is kind of one of my really main question. Follow on to the Mill et al. Paper. The real impact of spectral irradiance, long-term spectral irradiance on climate, on regional climate. How can we do more studies? What other data sets are available to do the study? What other data sets we might need to kind of understand, the downward transport of spectral irradiance into chemistry and all of that. That's part one. Part two is how do we bring the tools of AI ML in an agnostic fashion and see if we can even infer some of the patterns that have been informed from statistics and correlation studies. Thanks.
Yeah, starting with the second one. Well, I think the second one is the big question: how we can move forward to go beyond the standard analysis techniques, be it composites or regression, which is very often is being used, let's say, in this type of studies. I'm not aware of any work to that. There are some attempts, let's say, in order to infer ozone in the stratosphere and how well, ozone trends essentially in the stratosphere, particularly in the lower stratosphere. In the solar cycle, it's just a kind of background variability to that, but not so much on on having in mind the climate dimension. So for the X observations, well, I would like to. Most of the studies are bound to use what we have available, and this is essentially temperature, surface temperature, and perhaps we have some quality observations and reconstructions for 120 years, but that's all. Sea level pressure follows to the same directory, but particularly for the northern hemisphere. And particularly, we can go back in time with some reconstructions. I would love to have, something, a similar record on precipitation, because I think, the other, there are, besides the temperature, precipitation seems to be sensitive, let's say, and perhaps more sensitive to variations in the coming irradiance in decadal time scale. So definitely precipitation, but again, you can have proxies, indirect estimates from that in particular locations, but I'm not sure that you can use any how to move forward. The other thing, and this was very obvious from the SEAM observations, was the amount of UV variation over the solar cycle. And you're aware of this anti-correlation that the early SEAM observations show, and this sparked a lot of discussion about the effects on the stratosphere. So I think, bridging the gaps in the UV, it's equally important for the stratosphere in order to quantify, let's say, effects. If you want, let's say, to simulate how the stratosphere and effects in the stratosphere from the UV variation may propagate down to the surface.
Thank you. That covered one of the questions that had arisen as well, and I think the precipitation data is particularly interesting and related to what we're trying to do with this work. I think we'll follow up with that in the final collaborations ideas. So there's a quick question about the Miyake event signature, about whether that's due to SEP or GCR.
Well, it's actually it's both, because you deflect actually the incoming galactic cosmic ray, so you reduce the GCR, and you reduce, and you see actually in the time series you reduce actually the carbon-14. So it is, the short answer is the GCR.
Thank you. You mentioned, I guess we'll stay on this thread, and Ankush wants to know how anthropogenic and natural aerosols affect the climate. Do we know the relative importance with respect to other climate drivers?
Yes. Yes and no. I mean, we know, for instance, that the net effect of the anthropogenic aerosols is to cool. So the aerosols, let's say, counterbalance the greenhouse gases. Of course, there are many uncertainties on the amount of particular aerosols, how much the radiating forcing of them. And for instance, there is, and also the black carbon is a paradigm of that, and how much, let's say, the indirect or the semi-direct effects of the aerosols on climate, which is through the relationship linked to the cloud formation.
Thank you. You mentioned during your talk the tendency to scientific publications to publish positive results, which means they look for some effect and they find it. I am curious about what you see happening, or what you see the value in some form to publish negative results, where you set out to find some effect and you don't find it.
Yeah, well, I mean, I mean, this is a kind of personal story, because it's sometimes it turns out that it's extremely difficult to get anything meaningful from the simulation. When you are using a climate model, so I have to admit that you need to pile up a lot of ensemble of forums if you can detect that. And in fact, when I started, let's say, my PhD was about to study the stratospheric variability, but the model essentially we had was, wasn't able to do to simulate anything that could resemble the observation. So this was a kind of a negative. Of course, it's difficult actually to go through I don't know how much publishable is a negative result. So I mean, okay, negative result could be like the study I mentioned and I described before, is that its internal variability. There is no solar signal in that. Okay, perhaps this could be something that we could publish back then, that we couldn't, let's say, detect any signal. But on the other hand, will be the counter argument that, well, perhaps your model is wrong, and you don't have the right model to study the physics, and this is something that something it's correct. So in principle, publishing negative results is difficult, but for your scientific understanding, it's something I think that helps you in a perspective.
Thanks. That's an important discussion. Dan, I'll hop back over to you. I'm gonna archive a few of the questions that we didn't get to to Slack. Thank you.
Great. Thank you very much. Yeah, and on that last comment, I can appreciate that we had a very hard time publishing our simulations where we tried to reproduce the Levitska result, and we had that same response that we couldn't reproduce it in our model, and the same reviewers were saying, well, your model must be wrong. But it's an asymmetric response that it's difficult to counteract. Okay, well, thanks very much, Sergio. So we should move on, and our next speaker is Shannon Curry. Dr. Curry is a planetary physicist currently working on NASA and ESA-supported research projects as the Deputy Assistant Director of Planetary Science, the Space Sciences Lab at UC Berkeley. Her focus is on terrestrial planetary atmospheres, primarily in atmospheric escape and dynamics of Mars, Venus, and other weakly magnetized bodies. She is also involved in the instrument development and mission concept development for future flight exploration of the solar system. Her research relies on statistics, applied mathematics, modeling, and data analysis in order to better understand spacecraft observations of our own solar system. Currently, she is the project scientist on a Phase AB Simplex mission called ESCAPADE, a science team member of the Parker Solar Probe, and a collaborator on NASA's Nexus for Exoplanet System Science program. She will be the PI of MAVEN mission beginning in October 2021. And with that, thank you for agreeing to speak today, Shannon, and looking forward to your talk.
Thanks so much. I'm really looking forward to this too. This has been really exciting to get to share what we're really learning about big data and sort of the computational techniques at Mars. So we're sort of pivoting here a little farther out in the heliosphere. But with that, I wanted to just give people an overview of MAVEN in particular, because that's really the spacecraft we'll be focusing on today. And so MAVEN is the Mars Atmosphere and Volatile Evolution mission, and it's been in orbit for about 6 Earth years, which is about 3 Mars years. And we're right now over 14,000 orbits. Everything's nominal, and we are continuing to produce level 1 science measurements that are publicly accessible. MAVEN's in a highly elliptical orbit. And so right now our periaps is around 180 to 240 kilometers. And we've been doing different kinds of operations to make sure that we will decrease our fuel usage and effectively make sure that we can stay in orbit past 2030. Our apoapsis is around 4,400 kilometers. And so that gives us, again, that really nice elliptical orbit that precesses around the planet. We are also a relay for the Mars 2020 rover, and we help them with EDL. And right now we're doing a few relays a day. So it's not just our data that MAVEN brings down from our own science, but it's also from our landed assets as well. And last, I will be transitioning to the PI of MAVEN this summer. So hopefully I'll get to see all of you even more. Okay, so just a quick review. Again, data here on Earth, we have much more of, but thinking from, millions and millions and millions of miles away, you're looking at a slightly smaller data set. However, you still need those big data computational techniques. So just as a reminder, Voyager back in the 70s, we were looking at data sizes on the order of like 100 gigs. And once MRO, or Mars Reconnaissance Orbiter, went into, once they completed their orbit insertion, from 2005 till now, we're looking at something like 45,000 gigs. And so this is just a huge revolution in terms of how much data we're getting at Mars. And MAVEN's currently, we're just shy of around 10,000. So that's 10 terabytes. And we're looking at, hundreds of millions of rows, and we have 1 second cadence. And many of our measurements actually have, less than a second cadence. And so we have a huge data set and really specific kinds of data types to analyze. So with that, we have a number of instruments. So if you look in the yellow box on the upper left, this is the solar wind monitoring suite. So we've got SWIA and SWIA, so that's the solar wind electron or ion analyzers, SEP, which is a solar energetic particle instrument, and then EUV, which monitors the EUV from the sun. If you looked farther down in the red box, static, mag, and LPW, those are going to be looking at things more specific to the planet. So static measures the heavy ions, or ions, basically particles that are charged that come from the planet. Mag measures the magnetic fields, both the IMF and induced fields at the planet. And LPW measures things like waves and thermal distributions. And then finally on the right, those are our neutrals. And so IUVS measures basically sort of our neutral population, and NGIMS also does the same. And so we're able to have a really, really nice suite of instruments all around, all within, the spacecraft, and all of them provide really different things. So just as a reminder for those that are not as familiar with the Mars solar wind interaction, Mars lacks a dipole magnetic field. So Earth has a magnetic field. So if you have a compass, it points towards north, but Mars doesn't have that. But it does have these remnant crustal magnetic fields in the southern hemisphere. And so what happens is you actually get this hybrid magnetosphere. And those little crustal fields can actually reconnect with the IMF, or the interplanetary magnetic field from the sun. Additionally, because it doesn't have that magnetic field to protect the atmosphere, the upper atmosphere is directly interacting with the solar wind. And as a consequence, it's eroding really, really quickly. There are all these different processes that you can see on the right that affect sort of all these different dynamics, but we'll sort of just focus on a few today. Just some nomenclature, because I think I'll be talking a lot about things like sheath or pileup or solar wind. So if you look at these figures, the black would be the solar wind. We start on the figure on top. This peach is sort of the induced magnetosheath. And so it goes straight to the sheath because we don't have that magnetic field. The pileup, often called the magnetic pileup, and then you've got the wake. Now, often we consider the pileup and the wake, that's the induced magnetotail. So again, when we sort of analogize Earth's magnetosphere, it would be the induced magnetosheath and the induced magnetotail made up with that pileup and wake. And then finally, if you look on the bottom, one of the things that we're really going to talk a lot about, a decent amount today, are going to be the escaping population. So when you think of comets, things are sort of coming straight out the tail. And then precipitating ions. Precipitating ions effectively, depending on the direction of this electric field, which we'll talk about in a minute, basically all these ions precipitate on one side or the other of the planet. And so that helps us, there are a lot of different kinds of models that we can use to understand those fields. Just a little bit of AI nomenclature. I think this is a useful chart in that it tells us a little bit about sort of the subsets of sort of the big computational methods we're using. So AI, right, we've got any technique that enables machines to sort of mimic human intelligence. Machine learning, so often things like Bayesian inference, that would fall into the machine learning category. And so it learns tasks without explicitly programming them. And then finally, we've got things like deep learning. And deep learning is going to be something like a neural network. And that's going to have a number of different kinds of layers that you can learn representations and tasks directly from the data. You can sort of see a timeline here on the bottom from the 50s to the 80s. We were understanding machine learning. And as of, a little bit past 2015, some of the deep learning got really, really sophisticated. And obviously this is an exponential curve. So today with Mars, one of the really, there are so many fun topics to talk about with Mars, but in terms of machine learning, there are three projects in particular that we've really benefited from. And so I'll start with the first, which is called a solar wind proxy. So the solar wind is really important. MAVEN has this elliptical orbit, and to do all of the, to do all of the really cool science, we need to have the solar wind to understand the Mars solar wind interaction. And so the solar wind helps us understand things like the bow shock location, plasma turbulence, atmospheric escape, the ionosphere in general, and then something called sputtering we'll talk about at the end. You can see on the upper right, things like the solar wind really help us determine under different conditions, things like that bow shock shape. They also help us organize our data. So again, when we want to understand when certain electric fields, the background convection electric field is in play, we can actually transform our coordinate system into something called MSE. And that helps us organize our data, but we need to know what direction the IMF is to do that. So when we think about how we get the solar wind measurements, so generally speaking, you take a measurement in the solar wind and we go in orbit, we get our second measurement, and that's how we can effectively approximate or interpolate between those two measurements. However, there are times, unfortunately, when our orbit precesses out of the solar wind and we're just in the magnetosheath. So what's happening here is we no longer have access to what any of the solar wind measurements were. And orbit precession takes place. We will be out of the solar wind for weeks to even up to like a month or two. So we needed a way to understand what the solar wind was doing without just extrapolating from 1 AU Earth, because often there are a lot of errors in that method. So one of our colleagues decided to create an artificial neural network. And so what he did was he took a bunch of different solar wind parameters in the sheath. So again, this region back here, this region back here, and input the spacecraft coordinates and cylindrical coordinates. And so you can see here the cylindrical coordinates of the spacecraft, the solar wind moments, so the density, the velocity, the temperature in the sheath. Then we took the mag instruments, so our magnetic field, the magnitude, as well as those different components, and then our EUV, our Lyman alpha flux. So we feed those in, and we have two hidden layers effectively. And those two layers, the first one has about 24 neurons, and the second one has 12. And there are a lot of details we can go into, but effectively the output is going to be 7 you're going to have seven neurons on the output. And these are the things we really want. These are the solar wind moments that we can now use to understand what that solar wind Mars interaction is. So we get things like solar wind density, velocity, temperature, IMF, et cetera. So, okay. So if we go to our next slide here, what this group did was they took the ANN solar wind parameter accuracy and they wanted to try and understand what that was. And so if you look at that, what we're doing here is we look at around 5 days and we calculate the difference in the solar wind measurement versus what the proxy or what this output in fact calculated. And what we do is we define the accuracy as the percentage of the output, so the proxies that have a percentage difference of 50% or less. So if you take a histogram here, and if we go through, if you take a histogram of what all of those, the percentage difference are, 84% of those measurements then have a 50% less error in terms of their accuracy. So the accuracy of the actual ANN here is 84%. Now, this is for one of those outputs though. So if we look at each one of those, the outputs or the output neurons, what you're looking at in terms of our solar wind proxy, we can estimate the speed and the temperature and density. So those the solar wind moments pretty well. So this is a high accuracy output we're really thrilled with. The magnetic field, we do a pretty good job. It's around 79%. However, things like the cone angle and the clock angle of the IMF are a little bit more difficult. And so these are sort of moderately accurate. However, something is better than nothing when our orbit has precessed out of the solar wind. And so sort of the bottom line here is that the ion moments in magnetic field have pretty high accuracy, but again, things like the orientation of the IMF is a little trickier to predict. So if we actually look at, here is January 2015 through to the mid 2018. If you look, this is the solar wind measured versus what the ANN has produced. And so the white regions are what MAVEN has measured. And so you can see these gaps in every other column here in the measured. Right now, we don't have any measurements when you see where those gray areas are. But with a proxy, we can fill those in. So here in all of those red circles, you can see the proxy has provided really an enormous amount of data for us and during really important times, particularly things like during solar active regions, when you have like a CME or an SIR, basically like a space weather storm, propagate past Mars, having any kind of proxy is really, really important. So just to sort of summarize this work, please contact Saranga if you have any questions. He's done a great job leading this. And again, this ANN was done really, really well to determine the proxies for the proton density, speed, temperature, and then the IMF as well. So the next thing that's really exciting is a magnetospheric disturbance index. So what this group did on MAVEN was we want to try and understand, when we think about atmospheric escape, a lot of what we're thinking about is what's the sun doing to help drive that escape? And especially during, again, those storms or active, when we have solar activity, that enhances the atmospheric escape. And so what we wanted to try and do, similar to Earth, the way Earth has like a DST, we want to try and understand the strength of a disturbance from the sun and help us understand sort of what we should be expecting in terms of atmospheric erosion. So specifically, to make sure that we can actually say something about how disturbed a magnetosphere is, that requires a statement of what a quiet period looks like. And so what we want to do at Mars, that baseline is constantly moving. So what we wanted to do is, again, understand just generally how disturbed something is and compare it to what nominal conditions are. So this group has developed a magnetospheric disturbance index. But obviously computation by hand is really time consuming. So a neural network was a really, really nice tool for this as well. So what we did was start with 2 parameters. So an enhancement of the magnetic field, or so that absolute magnitude, and then looking at the variability. And so what you can do is take an FFT around the proton cyclotron frequency. Basically, this just means you look at how much the magnetic field is varying. You normalize those quantities. And again, this is in the magnetosheath, not the solar wind, because we don't always have solar wind measurements. So we look at it in the sheath. And then you compute, we call it the MIDI. You can compute this magnetospheric disturbance index by the summation of those two normalized enhancements. And that can start to tell us about the kinds of events we're seeing as they propagate past Mars. So one of the famous ones, and we did a special issue on this, was the March 15th ICME. So it's an coronal mass ejection. So this was this huge storm, hit Mars, and this effectively what we're looking at here are the top two panels are, you're looking at the SEP observations, so the solar energetic particles. That second column, that's the SWIA observations. And so you're looking at effectively like the ion fluxes here. So you can really see an enhancement right here in the middle. And then finally, you can see the mag measurements on the bottom panel. And this is where the storm is. And so the bottom line is that the magnetometer observations are really, you see a huge enhancement when you have these space weather impacts at the planet. And again, I know space weather is not everybody's favorite term, but when you have these, when it's this kind of solar activity, the magnetometer is incredibly sensitive to. So with that, what we can do is calculate the MIDI for 4 days around the event, because we want to get the sort of quiet conditions versus the enhanced conditions. And so you can see the MAVEN observations are the blue dots. You can smooth that observation. And actually there was a second, if you look this little second sort of shoulder here, there's actually a second like mini CME right after. And so you can see that here. And then the red line is the Gaussian fit for this. So what we can do is now we can do that for over 70 events from 2015 until 2018. And when you do that, you can start to see, you normalize it as a function of time. Then we can look at the duration. We can look at basically the MIDI index number and as a function of time. And here you can see a histogram of how many events we have. So with that, here's where we can take the neural network and say, okay, we'd like to do this across the mission so that we're not going by hand to do all of this. So we have two hidden layers, the convolution layer, the decision layer, and those inputs are a little similar to the previous one. So we have the spacecraft position, we have our magnetometer observations. So we've got the strength of the field, and then basically that FFT, or sort of that variability in the magnetic field in the sheath. And then we're looking at different kinds of electron analyzer observations. So we look at 4 different channels of electrons, so 4 energies of them, just to make sure that we're actually in the sheath. And then with this convolution layer, this helps us understand if there's a pattern in the series. It looks around 30 time steps, and then we have a decision layer. And so if we go here, the data set is split into about 70% training and 30% validation. Whereas with the SolarWind proxy, we did an 80-20. And I think that highlights, with neural networks, there are a lot of knobs to turn in all of this. So sometimes results can vary. But in this particular case, we used a 70-30 split. And if you look, you can see that we trained over around 100 different epochs. And effectively, if you go more than that, the neural network can memorize basically the inputs. And then so the outputs actually, the accuracy here in orange degrades really quickly. So 100 was sort of the sweet spot for us. And so as you look, as you increase the training with the validation data, you can see the accuracy increases. And so this is around 90% accuracy, sort of using the same approach that we saw with this with the SolarWind proxy. And so again, a lot of different knobs to turn here. However, this was a really exciting way to start to assign an index to these different things at a weakly magnetized planet. And so this is the final result. We're actually working to color code this with the with basically which specific events we've identified, especially using NLIL and the 1AU measurements and comparing. But you can see we've seen a number of really disturbed periods, and almost all of these correlate to storms. So co-rotating regions, co-rotating like interaction regions, or things like coronal mass ejections, and even flares. We see like that really, the flares are often associated with all of those. And so here you can see over the course from 2018 that you see this really exciting set of data now that we have with an actual disturbance index assigned to. And so this body of work was really exciting for us because we were able to achieve 90% accuracy, and you can apply this to the whole data set. And even though there are a lot of knobs to turn, we can start to understand things like how seasons and what the solar minimum conditions look like. We can start to compare a lot of different times now to understand what the trend in that disturbance index is. And going forward, we can apply a method like this to another weakly magnetized planet like Venus, even potentially Titan for some of the outer heliospheric bodies. Okay. So one of the last projects that we're going to talk about today in terms of using machine learning or neural networks, in this case, Bayesian inference, is the magnetic field structure around the planet. So one of the big questions we've had is, we have the planet and we've got this induced magnetosphere. And so all these things are changing. We know that the solar wind and the IMF change on the order of seconds to minutes. So how do we start to disentangle all of these different effects to understand what the induced magnetosphere at Mars looks like? So things like the morphology and the topology of those magnetic fields. That's particularly important because understanding the induced magnetosphere helps us understand how particles are accelerated out. And so really, it's the big picture of the magnetosphere directly influences things like atmospheric escape. And that helps us understand the evolution of the climate. So how do we disentangle all of this? So another one of our researchers, Abby Azari, started with the first thing was trying to understand how do we organize the data in the first sense? So, how do we quantitatively do that? And then the second component was using this Bayesian inference or an interpretable model to quantitatively understand what the results are of the induced magnetosphere responding to the solar wind and the changing IMF. So the first thing was she actually created one of the first SQLite 3 databases. So this is searchable. And so she used the publicly accessible Maven data. So there's level 1 and level 2 data products that we put out through PDS. And then she also used the things like our solar wind proxies. So the non-publicly accessible data sets, although those are probably going to get released soon. And so she put those into this database and then was able to create gridded data products. So that's a net CDF4. And that really helps us organize the data in a more understandable way. And I'll show you an example. So one of the use cases is looking at the magnetic fields at a certain altitude for certain solar wind conditions. So here, if you look on the left, this is just an altitude. So we can look at any given altitude, outside of the bow shock or beneath the bow shock. And this is effectively looking at the crustal magnetic fields. And so for a given IMF direction, the next thing you can do is you can look in the opposite IMF direction because that's part of this gridded data structure. And then finally, you could move up in altitude and do the same thing. And so this helps us with this global grid of magnetic field data start to suss out different things like different influences and how the system is responding to all of these time varying and spatially varying components. So if you look at the quantification of how we would do that, Abby used Bayesian inference to do that. And so what we started with was she gridded 6 latitude bands over the day side of Mars. And by doing this, she was then able to think about her prior understanding of the magnetic field distributions. And given a certain sample size, with the Maven data, then start to understand each of these latitude bands will respond to the solar wind differently. And using Bayesian inference, we can sort of quantitatively understand how. So if you look at this bottom panel here, you can see that something closer to 0 is going to be unaligned with the solar wind. So you don't see a lot of correlation there. Something around 0.5 is effectively non-responsive, and something closer to 1, you're going to see, okay, this is highly aligned. So in this particular case, you can see that in the northern hemisphere is much more affected by the solar wind because you can see this dark region closer to 1 than the southern hemisphere. And that's because of these crustal fields. The crustal fields effectively are, because of so much reconnection, and there are a lot of other factors, we can start to understand, okay, the northern hemisphere where the weak fields are, that's where the solar wind has the greatest influence. That tells us that, so there's a lot of other physics happening in the southern hemisphere. And if you were to look at a global map of all of this, here you can see this is the solar wind influence as it increases with altitude. And so if you look at her color bar, blue would be you're aligned with the solar wind. And so those are highly correlated. And then red would be it's unaligned. And so here you can see these strong crustal field regions in the southern hemisphere in this induced but hybrid magnetosphere. There's a lot more to learn about what's affecting them and what the structure is there. And so things like this is one of the really important tools in terms of thinking about how machine learning can help us understand that. This is an ongoing and I will say unpublished work. And so Abby's working to get that out the door soon. And also to use this tool, especially the gridded data set, to analyze a number of different things. So that's really important. And then finally, this is one of my favorite topics. It's a bit of a unicorn. So far we've used artificial neural networks in a really clever way to understand the solar wind proxy and magnetospheric disturbance indexes at Mars. And then we've also used Bayesian inference to understand magnetic field structure. These are all things when either the orbit is not in the solar wind, or simply we want to try and understand and disentangle things like seasons, dust, or just changes in the solar wind. But right now, there's a big question that we have. We have a lot of big questions, but one of the big questions we have, we don't have a tool yet to understand, but we know it's happening. So sputtering. Sputtering is when you get these heavy ions. So these are charged particles from the planet and they crash back into the atmosphere. They start to gyrate around magnetic fields, but they crash back in or precipitate. And what they do is then they collide with some of the neutrals and effectively splash out. Some of them with enough energy, they exceed the escape velocity and they can leave the planet. And this is a really exciting form of atmospheric escape. And so I think of it sort of like if you take a penny and you throw it in a pond, you get a little drop. But with the heavy ions from the planet, it's going to be a little bit more sort of like this very graceful polar bear. You're going to splash all the water out of the pool. And that's a really important process. So when we think about the precipitation and sort of the physics of what's happening, there's something called the background convection electric field, and that's the cross product of the solar wind velocity and the IMF. And what happens is, depending on the direction of the electric field, precipitation happens in the minus E hemisphere. And this can reverse. Often the electric field is pointing the opposite way. And in that case, the particles would effectively be precipitating in like a mirror image, so the exact opposite. And this is what drives sputtering. So the things to identify sputtering are going to be correlation of those sputtered neutrals with the precipitating ion fluxes. So what we want to do is take those ions that are splashing in and measure how much of it, or the flux, what's incoming. And then we look at the sputtered neutrals, and especially something like argon that's inert. Argon's not reactive, unlike oxygen, which is highly reactive. So basically, when you see enhancements of argon, you know it had to be through sputtering because it's not going to be sort of produced or accelerated in any other way. So we want to take a look and we want to correlate, okay, that sputtered neutral or argon with those ion fluxes, or we want to correlate basically with the IMF direction. Again, in that U cross B term, if we know that we see an enhancement of particles in the minus E hemisphere, that would also be an indication of sputtering. And then finally, we could do that with the solar wind strength. If you get a huge storm and then obviously you see this huge population of argon in that minus E hemisphere, that would be another way to identify sputtering. I want to stress the importance of sputtering because our approach is to observe these ions that drive these enhancements in the neutral densities. So these things that are going to get splashed out of the pool. We believe that sputtering is responsible for most of Mars's early atmospheric loss, but it's never been observed at Mars. In fact, it's never been observed in any planetary atmosphere. And this is atmospheric sputtering, not surface sputtering. But atmospheric sputtering has never been observed. So it's this unicorn.
However, we know it's happening because what you can do is, I won't get into a lot of the details, but mass fractionation of argon isotopes tell us that argon was removed from the upper atmosphere in large quantities. Again, argon really can't be removed in any other way other than through neutral processes, and it doesn't escape photochemically. So it has to be sputtering. And with that said, if we know at least around 65%, and again, these are sort of different fits, but if 65% of argon was removed during the sun's sort of really active early period a couple billion years ago, this is a really, really important process for us to try and understand. And so what have we tried? So far, the top, I'll go through this. So the top panel is on the blue is the argon density. And on the red that's the static heavy ion flux. And so when you plot them both over the course of a couple of years, you think, okay, well, that's a nice trend. I clearly see something. But if you look at the second column, or excuse me, the second row here, it's the mean density versus the solar zenith angle. Again, with one spacecraft, that orbital bias is always something you want to check for to make sure you're not sort of seeing things. And so here, all of a sudden you realize, okay, this might be a function of where the spacecraft is and where it is observing things. The solar zenith angle tells you if you're on the day side or the night side, and things statistically happen much more often when you're on the day side. So solar zenith angle closer to 0. That's where you're going to see more fluxes. And so we thought, okay, that's not great. And here's the LST. That just gives us the season. But it looks like here the solar zenith angle and O+ are directly related. So we thought, okay, we'll plot argon versus the static flux, and hopefully we see a nice correlation. Obviously, this is a total nightmare, and we don't. So this is where we started thinking like, okay, we can't just, use our simple sort of linear correlation stats and plots. This is going to take a little bit more. Okay, so what else do we do? What we can do is then say, what about if we look at argon density as a function of time and during sort of extreme solar wind conditions, and then we plot it? That doesn't work either. So actually using Jacob Grusbeck's, that NITI index, we can look at all the really big enhancements. And even during those enhancements, we still don't see much of a correlation. So this didn't work either, which is unfortunate. So then finally, we started plotting more and more and more and trying to understand, what are we going to do here? So looking at the distribution function of, argon, or basically correlating those heavy ion fluxes versus argon as a function of solar zenith angle or season. And when you look at all of these over the entire mission, this is crazy. You can start to pick out certain time periods when you might see a correlation during a certain season, or you sort of see things as a function of certain solar zenith angles. But we've tried a lot of things, and we're sort of at a loss. So then we said, okay, what if we try correlating? Remember we talked about the electric field. So in that -E hemisphere, what if we try and take a look there? So if you look in this bottom hemisphere in solar electric coordinates, you think, okay, if you sort of look carefully, it sort of looks like the southern hemisphere has, okay, I could maybe see an enhancement. And again, this is orbital bias. This is the data density. And here you can see that exact same pattern. So this is not an effect of an enhancement in, it's not that it's showing where all the precipitation is happening in a certain hemisphere. You see enhanced neutrals. We're not seeing that. Again, that's the orbit, unfortunately. So then finally we thought, let's use a time lag correlation. Maybe what's happening is the ions precipitate, and then rather than instantaneously, like a day or two later, or maybe it's 12 hours. So we tried time shifting and using different kinds of time lags. And no, unfortunately, we're not seeing anything, especially when we see in blue, this is that oxygen precipitation, and in orange, that's that argon column density. Especially when we see drops in the precipitation, this is anti-correlated. Now you see an enhancement in argon, and you think, I don't know what to do. So this is my pitch. Please use Maven data and help us. I think that there are some really, really exciting tools out there that could help
suss this out. And again, this is something that's never been observed before. So I will give you an invited talk to any of our PhDs if you can help us out and figure out this problem, because people tell me it's a unicorn, but we know this is happening. We can see these argon isotopes, and we know for a fact that there's got to be a way to observe this. We just can't figure out how to correlate it. So if you're good at statistics or you have a cool model to use, contact us. So to summarize where we are with everything, Maven's a really exciting target for applying AI techniques. So that's going to include, again, general artificial intelligence, whatever those tools are, machine learning, so those Bayesian statistics, and then things like the deep learning or neural networks. All of those are really exciting areas. And we have enough data that we're starting to uncover exciting trends and answer important science questions in order, with these tools. And as a review, again, Abby Azari did a lot of work sort of disentangling some of the spatial and time varying physics using those Bayesian stats. Jacob Grusbeck did a lot of work with this MDI, or magnetospheric disturbance index, and using deep learning. And then finally, Saranga was able to work a lot with our solar wind proxies and can provide us critical solar wind measurements during times the orbit is no longer in the solar wind. And sputtering, yet to be understood, but I'm quite positive that we can find a tool to help us out here. And so again, understanding the solar wind and its interaction with not just Mars, but other terrestrial bodies is really critical for understanding how planets and their atmospheres evolve. So these tools have been enormously useful to us as a mission. And with that, I will take questions.
That was great. Thanks very much for giving us some real hands-on examples of how you've applied these techniques to analyzing your data. I'm sure we have lots of questions in the chat, Ryan, but maybe I can sneak one in before we start. You mentioned something about dust and seasons, and I'm just wondering about, have you seen signals of what's happening in the lower atmosphere impacting things, escape processes higher up, and it's not just all coming from the sun?
Yeah, it's a great question. Absolutely. And so Mike Chaffin has done a lot of work on our team in trying to understand what the role of dust in escape is, especially, those lower atmosphere dynamics, and how does that sort of percolate up the physics? How does that sort of figuratively and literally percolate up to the top? And he's done a lot of work on understanding how dust can actually increase the amount of hydrogen and water in the atmosphere and what's escaping. And we're trying to understand more about the physics of why that's happening. And so once we got enough data to start to understand the Martian seasons, right? Because again, we've only had almost 4 Martian years there. So we don't have a huge sample size yet. That's just what happens with the outer, planets with larger orbits than ours. But looking at those dust seasons, yes, we have been able to measure that we see an increase in actually the water, which was fascinating, and particularly in the hydrogen. And so he used IUVS, and so that's ultraviolet scans to sort of measure that and look at those column densities. And understanding why is something that we've worked a lot with other missions on. So for example, TGO has been looking at this as well. They don't have quite as much data as us, obviously, but that's a great example of a collaboration with another mission where we've been able to piece together lower atmosphere measurements, upper atmosphere measurements, and then sort of what those seasonal effects are. And so now, to be totally honest, I don't totally understand why dust is driving an enhancement in water, but Mike Chaffin is at LASP at Colorado, and please email him. He's done I think 2 papers on this, and they're really fascinating results. Because again, water on Mars, why dust? I think of dust as dry, but that was one of the really cool results we saw once we were able to tease out seasonal trends.
Cool. All right. Thanks, Ryan. I'll turn it over to you. Thanks very much.
And thanks for a fantastic talk, Shannon, really engaging. And one of the cool things from my perspective has been just to witness the Maven team from afar and just the constant innovation that has come into the data analysis there. I think it's just kind of a shining example. So I certainly applaud your efforts and look forward to what you have planned ahead. So we do have some really excellent questions. The first one that I'm curious about too is how many space weather events exist in the MAVEN database? If we're talking about flares, CMEs, storms of some sort.
I think my list, so Christina Lee has done a lot of work on this, and we're about to publish a paper on this. I think we're north of 90 events. Now that includes things like stream interaction regions, and space weather is not your thing. That's when the sun's fast solar wind and slow solar wind effectively like kind of collide, and you see this really like enhanced region. And so those happen a couple times a month just by nature of the way the solar wind rotates or the way the sun's rotating. But we've had two special issues on major sort of space weather activity. So the March 15th ICME was one that was back in 2015. And then in 2017, we had the September event, and that was a CME, a flare, and then because we're at 1.5 AU, the whole thing like merged with an SIR or stream interaction region. So it was just, it was really exciting. And so I think we're looking at around, I think between 80 and 100 events. But those two in particular were really studied with like a fine tooth comb. And we did, I think we've probably done like 20 or 30 papers on just those two events alone.
Wow, very cool. Some counting statistics there. So Ankush wants to know, what are the new processes that are encountered at Mars that we may not see here at Earth in our magnetosphere?
Such a great question. So new processes, those are going to be things that really are going to be unique to Mars's hybrid magnetosphere. And so because we have those, I say we loosely, me and the Martians, these crustal magnetic fields, these strong fields in the southern hemisphere, you get some really cool kinetic physics there, particularly with reconnection. That's something we don't see. And I think actually that's something that I've been on a couple of different committees now. We're trying to understand how would that potentially impact any kind of like human presence there in particular, because you get these sort of almost like magnetic bubbles everywhere. And with reconnection, does that create sort of like a shield in terms of radiation, or does it not? And so one of the really neat things is understanding that hybrid, basically in particular those remnant crustal magnetic fields. That's something we don't have. We really don't have an understanding of here at Earth. And it'll be interesting to see increasingly, especially in our collaborations with the rovers and the NSL RAD team in particular, we're trying to understand that's one of the big areas where we're trying to correlate, okay, how does that help us or does that actually hurt us? And those results are still TBD.
Very interesting. One of the things that has been studied extensively here at Earth is how much of the solar wind energy enters our magnetosphere. And this is something, a question that has implications for exoplanet research as well. And do we have an idea of that quantity for Mars?
Yeah, I mean, in terms of, I don't know if you want like an average flux, if you want 3.4 or 10 to the 7, differential energy with protons, but which is about the average. But in terms of, we know what during solar minimum and solar maximum, we more or less have an idea of what those moments look like. And so that's a way to think about energy input to the system. It's, for example, solar minimum, you're looking at around between 200 to 300 kilometers per second for the velocity. During solar maximum, it could be up to 400. If you compare that to something like Venus, if we're talking about trying to compare things, at Venus, it's about 100 kilometers a second faster. So that's during the same exact time, that's significantly faster, even if, the difference between 0.7 and 1.5 AU. So when we think about exoplanets, the first thing is you say that's assuming a sun-like star, right? But then, depending on where you are on that main diagram, right? In terms of stellar type, you think about something like an M dwarf, and M dwarfs, which are the most common type of star in the universe, those M dwarfs really crank in terms of the solar wind. So I think if there's some in fact, I think one of the talks later today might include a little bit about this, but some of those like stellar energy and sort of solar wind fluxes, you could be talking about like 1,000 kilometers a second or 2,000 kilometers a second. I mean, you're talking just about huge numbers. And so atmospheric erosion would crank into like the hydrodynamic regime at that point. And so you have a whole different set of physics. So I think one of the really cool bridges between understanding, exoplanets is thinking about like how our star affects even just different planets at different places in our inner and outer heliosphere. And then you think about different kinds of stars do that as well. So a lot of moving pieces, but even just comparing Mars energy input to something like Venus, because Venus is also weakly magnetized. That's a really great starting point. And even there, you see a pretty big difference in solar wind inputs.
A lot of fascinating areas for research. Along that line, do we know what the dominant physical process is for this solar wind magnetosphere coupling at Mars?
Dominant process. I mean, there's a dominant escape process right now in terms of the atmospheric escape and the way the atmosphere is slowly being eroded, and that's photochemical. And so what happens there is basically you get charged particles or ions, and they can photodissociate. So basically energy comes in, you can lose an electron, something becomes charged, and then basically through collisions, something like oxygen will gain enough energy that, they're different branching ratios. This is like a whole section at AGU, but effectively a handful of those particles will actually gain enough energy to then escape. And so photochemical escape is an order of magnitude higher in terms of the escape rate than ion escape, which is next. Now that's present day. When we crank back in time and we use different models, and these more models that are things like hybrid or MHD, magnetohydrodynamic models, when we use those types of models to understand when the sun was more active and you had more of a solar wind, so again, that 1,000 kilometer per second kind of velocity, that's when sputtering just crushed them all. So again, my unicorn still stands. I invite the entire community to help me with that problem. But present day, it's photochemistry that really is removing the bulk of the atmosphere at Mars.
A grand challenge. I love the provocative term, the unicorn. I think that should get people excited. I know it does.
I hope it does. It's real. I know it is. So please help me find it.
Yeah. So Ashna is asking about the green light emission at Mars. She wants to know how the aurora happened at Mars is different from the green light spotted in the atmosphere of Mars. And will the green light help missions related research? Does it give information about the density at Mars? And Ashna, I apologize. I'm not sure if that's a male or female, so I didn't mean to place something on it.
They will thank them for their question. So that's one of the other really cool things at Mars. So using IUVS, our ultraviolet instrument, we have found diffuse and discrete aurora. So those are basically, diffuse aurora happens sort of all over the planet, and then discrete are these really localized areas. And effectively, auroras, right, are the result of particles moving down the magnetic field. And so what happens is then they get excited and emit these different spectral lines. And so in terms of will that help other missions? So EMM, which is a UAE or United Arab Emirates, it's their HOPE mission, in fact, and that's at Mars. And that's going to be trying to look at some of that as well. I think that the green light, I would say in terms of, does it help, does it inform other missions? I think it's a great place for collaboration. So I think when we observe aurora, whether it's diffuse or discrete, that's something where, for example, ground campaigns, it's really exciting to look. I know at Venus, Candace Gray has done a lot of work on looking at some of those green lines, and effectively, if you can coordinate the ground any observation of the aurora with others simultaneously, you can start to really glean a lot more information about, you're right, how much density there is, what the field strength of that magnetic, what the magnetic field line was. And so that does certainly help. But again, that's where knowledge of the solar wind is really, really helpful, because then if you know that you're seeing a huge enhancement, solar activity, often we see a strong correlation in auroral activity. And so that's where sort of the sun, everything, the mud to the sun problem at Mars, you really need all of those observations simultaneously. So I would, to answer your question, hopefully, yes, it informs us about what some of those like there must be enhancements. It does inform us. And then it's also a really great opportunity, if you can, to use ground campaigns to help observe some of those aurora.
Yeah, really cool. I mean, there's getting to be some sort of constellation and of ground and space-based instruments at Mars. Do you talk with those other missions? How do you coordinate?
So there's a Mars program office. So JPL has a Mars program office, and then NASA headquarters has Mars exploration program. And obviously Maven is part of both. And so we actually just started a space weather, like it's not like a super secret email, but we do have we have a special alert system, and we have points of contact at each of our Mars assets. And we send an alert every time we actually see something propagate at Mars, because at Earth, we might see something, but remember in the heliosphere, sometimes we're on the other side of the solar system, on the other side of the sun effectively than Earth. So Earth and Mars can be like counteraligned. In fact, that's called solar conjunction, when they're actually completely unaligned and the sun's blocking them. And so even though at Earth, we might have an idea through our models, and I know we heard about that earlier today, things like, solar flare and CME predictions, they're still predictions, and those are for Earth. And when we're not aligned, it's hard to know what's coming at Mars. And if we actually, got the tip of an ICME, or, it propagated us like face on. And so we have a special alert system actually for all of the Mars assets. And that's sort of how we communicate. But generally speaking, usually the space weather community, we all talk a decent amount. If there's a lot of activity, everybody starts chatting. Everybody gets really excited by sunspots because we were in a really deep solar minimum. I think most of you know that, but it was really quiet, like really quiet. And so now, like anytime anything happens, we sort of like are popping bottles to be like, oh my God, there was a CME near us. That's great. So, especially with the ascending phase of solar cycle 25, we're really excited that hopefully we see more things and can share that data real time with folks.
Yeah, and it's really exciting just because I think it's a nice proving ground. If we ever want to put people in orbit about Mars or on Mars, we're going to need some kind of alert system like that. So thinking through that space now is really interesting.
Yeah, I definitely think increasingly, I think heliophysics and planetary, and particularly the Mars program, are trying to build as many bridges as possible. And actually, Jack Eddy, this is a great forum to do that, to start to think about their tools that we can all use. And a lot of these topics are just really interdisciplinary, as I think a lot of people have said so far. And so we'll certainly need that for any kind of human presence.
Yeah, that's something we should record in the final collaborations ideas. I would love to see that be an outcome of this meeting.
Absolutely.
So speaking of space,
can I just add a point to that? I had written it in the Slack, but I wanted to actually, for the folks who are online, take a look at CPAESS heliophysics resources that has as its fourth book, Comparative Heliophysics, which was really meant for these kind of topics, going beyond Sun-Earth connection. And thank you, Shannon. That was a very awesome talk.
Thank you. It was fun to give. People don't usually willingly ask about the kind of models you use. And so this was a great chance to showcase some of the really cool tools.
And I just want to squeeze in one other question at least. Did Maven observe any SEP events during the cruise phase before September 2014?
Such a good question. So the cruise data, I can't remember, I should know. I don't remember if all of it's publicly available. There were one or two events that we were able more or less to see. However, that's something that, the instruments were still really being calibrated. And so even though we were on the declining phase of solar cycle 24 and things were actually really active during cruise phase, that is something that the calibration was not all there. So I don't know that all of it's been released. However, I am 90% sure that we did see a couple of SEP events.
Very cool. I guess the final question here is about the use of the Bayesian inference. I know that one of the things you get from that kind of approach is uncertainty bounds. Was that used in a study?
Yeah, I actually skipped over that slide because it's it's like its own hour-long talk. So there's sort of different, you can use sort of like binary components, or you can sort of, yes, there's a lot of uncertainty with the Bayesian inference. And so I'm trying to think of how to answer that. I mean, I guess the short answer is yes. There's quite a bit of uncertainty. However, that's one of the things we're slowly trying to work towards understanding, what are the different weights, and effectively, how do I put it? We're trying to do a better job of understanding, especially some of like the inputs and effectively like training data, like how do you teach things? How does the algorithm learn? And so that's something, how much data you use is also sort of tricky, because you don't want, there's sort of a saturation point, right? So that's definitely a work in progress at the moment. But feedback is welcome on any of that for those of you that are using Bayesian inference at the moment.
Yeah,
I'd love to talk more on Slack, especially about some of the details. I'm trying to think of how to summarize them, not in an hour.
Yeah, I'd love to talk with you more about that. And thank you.
Yeah, I can put the details in the chat.
And also about the point of just understanding how the models are learning. I think there's a lot of kind of haphazardly maybe applying machine learning and not really understanding that there's a point at which models may become insensitive to new data and stop learning from the information you're providing to it. And so understanding that is very important.
Yeah, the ANNs, I sort of blew past that too, but even just, again, looking at those weights, looking at which kind of transfer function you use, and then even things like, the number of neurons, at some point, the accuracy saturates. And then even like the training data, eventually the training data can memorize things. And so, I mean, granted, that's ANNs, not Bayesian specifically, but there are a bunch of different knobs you can turn, and you realize there's a lot of trial and error in area for improvement.
Yeah, completely agree. I'm going to take the opportunity to just make a couple of quick points on that, just because I think it's very important for this community.
Yeah.
One is machine learning is inherently an optimization and a focus problem. So where are we placing our focus, and how are we actually exploring the massive space that are these models? And two, one of the ways that I think we're going to see our field move, and I at least hope we see our field move, is the loss function. So what are we optimizing for? We're going to get these models that find a solution, but is it what we're actually expecting or hoping to get from the model? And so the loss function really is what determines that. So I hope people will play around with how to build science and physics into the loss function.
Physics all the way.
So I think we're coming up on the end of the time here, and just want to thank you again, Shannon. That was a brilliant talk, and all three of the talks this morning were fascinating and engaging. So thank everyone and all the participants as well. Hand it back over to you.
Thanks so much for having me.
Thanks, Ryan. Yeah, this was a great session, and all the sessions have actually been fantastic so far in this meeting. This goes to the end. This session, we have a break now from 11:30 until 1, and then our parallel sessions start at 1 o'clock. But I would like to encourage everyone while they're having their lunch break, or maybe their dinner, depending on where they are, to spend some time on the Slack channel providing ideas. I think that we're going to have a meeting of the SOC, the Science Organizing Committee, around 3 o'clock, and try and distill what input we get there to define a few preliminary groups for breaking out tomorrow. So please get your input in there. Turn all of this great enthusiasm with these questions into some concrete areas that we can look at in the future. So thanks to the speakers again, and we'll see you in an hour and a half. Okay.